one was... Okay, so I guess I lost track of the other thing that was asked yesterday. So it will, sorry, the second part I was asked yesterday is also about more connection between the linear code and the lattice itself. So I will show more of how the parameter of the code actually influence the lattice. So that will be the first part of my talk. And in the second part of my talk, I will try to give you some motivation why you may be interested in looking at this construction these days. And I will give you a list of applications, but I will go into detail of one, which is actually application to lattice-based crypto. Okay, so the first step is, okay, we want to define a construction A using construction of lattices from number field. So in order to do that, we need to remember what was the key ingredient. So when we started with the simplest variation of construction A, what we did is we started with the integer z, and we define this reduction modulo some prime. On my first example, it was modulo 5. So if we want to do something that involves number field, the principle of construction here is to look at the pre-image of some projection. So we will need to figure out what this projection is. So I will give you one example, and the one example is actually following up some of the example we computed yesterday. So yesterday I described this structure. So zeta 3 is exponential 2 pi I divided by 3. So it's a third root of unity. It's a complex number. And so we saw that we can look at this set z zeta 3, which is given, so let me write it, by a plus b zeta 3, a and b are integers. Okay, so this is our context. So now, if I want to be able to get a construction A that will go from z to a number field, say here z zeta 3, I need to find a suitable projection map. So in the case where we were working with z, a natural candidate was to take, for example, here 5, or more generally, p a prime. The reason for that is because when we work modulo p a prime, what you get after projection is actually a finite field. So we can work with our favorite linear codes over finite fields. The same principle will hold if we go from z to z zeta 3. The guiding principle to define this map pi is actually to do the projection modulo something. And we want the modulo something to be such that the end result is actually a finite field as well. Just to be clear here, this is somehow a choice on my side, because I'm interested in looking at codes over linear codes over finite field. So at this point of time, if you are, say, looking at codes over rings, probably you want to be a bit more general in which structure or which ideal you are taking to take your quotient, because you want to obtain a ring so that then you can see what's happening when you build your codes over your finite ring. But for my purpose, I really want to have a finite field. So what I will do is I will take the equivalent of a prime number for the integers, which is I will take a prime ideal. In my example here, I will take 1 minus zeta 3. And so once I do that concretely, so it gives me so one may want to work a little bit to show that when you do, you look at the zeta 3 modulo 1 minus zeta 3, you do get a finite field, which is F3. There is, of course, a general theory that explains why this is the case, but in this case, it's simple enough that one can actually just do the computation. And so, for example, I have shown here a little bit how it works. So actually, if you look at an element a plus b zeta 3, so you can also write it as just, you write your third root of unity, minus 1 plus I squared of 3 divided by 2. And then what you can do is you can split the real and the imaginary part. So the real and the imaginary part, what it tells you is it tells you how I obtained the grid, which is here, how I have given a representation in R2 of this zeta3. And if I look, on the other hand, at what this projection does, well, it actually sends, so we are looking at what happened when you apply pi on this quantity here, and modulo 1 minus zeta3, well, basically, this is saying that in the quotient, 1 minus zeta3 is actually 0 in this thing. So the map, actually, what it does is it sends a plus b zeta3 to a plus b. So once we figure this much, we can actually understand how we can take, we can also visualize and understand and both visualize how you can take your, again, two-dimensional grid here and map it to your 3-point here. So here you can already see a slight difference with respect to the previous construction, somehow in terms of dimension, if you wish. So here you really have one copy of z and you get one integer. Here we actually really start from z zeta 3, and out of one element, a plus b zeta 3, we get a single element in F3. So this is just saying that from the moment you replace z by another structure, all you really care about to define a construction A, you need to take modulo a suitable something. So in my case, it's a prime ideal. Okay, so once you have that, you can actually exactly do the same thing as the normal construction A. So you can take a linear code C. Okay, so I have to be more precise. So in my example, I was using with zeta 3, I was using the ideal 1 minus zeta 3 to take my quotient. So I was looking at the projection modulo 1 minus zeta 3. So you can do that in general. So you just set zeta p, and then you take the ideal 1 minus zeta p. So that's one of the nice things with cyclotomic field. It's one of these very rare family of number field where you have really a whole family. So you can really parameterize things with a given prime and have result that holds for all those primes. So that means that in general, so here when p was equal to 3, when you take modulo 1 minus zeta 3, so we were working over F3. In general, when you work with 1 minus zeta p, you will be working over Fp. So given the linear code, so now once we work over Fp, so we have one copy, so one copy of this thing here give us one FP. So in order to have our code, what we will do is we will take a bunch of copies of this thing, exactly as before. So you can see that you just replace copies of z by copies of this thing, and we are going to have the following map. So now what happens is you mimic the construction A as before. So now you take a linear code, well, which is as before in this FP to the n, choose it of the dimension that you want. And now pi become the component-wise reduction, but instead of being modulo p prime, it's going to be modulo 1 minus zeta p, which is also a prime, for a prime ideal in this n copies of z of zeta. And then, well, exactly as before, you can actually look at the pre-image of your linear code, and you actually get that this forms a lattice that you can see in Rn. And here we will use the abstract formulation on how to describe the gram matrix by saying that this is actually the trace form, that with the normalization with a factor of p, which actually define the gram matrix over lattice. Okay, so one, I guess, visualization that I try to do for that is that in this particular case, it's illustrating the fact that you actually need several copies of your, well, in that particular case, ring of integer. Each copy gives you one copy of your finite field. So then you get your FP to the n here, and you can build your linear code inside. Okay, so to give a simple example, you could say, okay, so I'm going to take the repetition code, so I'm not very original, so I will just say, okay, so I have my map that sends it zeta 3 over my alphabet F3. Here I'm going to take again 3 copies of F3. So then I just need to get a linear code inside. So I was not very imaginative. I just pick a simple repetition code. And then, well, this construction A tells me that when I look at the preimage of the repetition code, I'm getting a lattice. How is my lattice described? Well, here I'm describing it at first without like more enough by definition. So it's just a bunch of vectors that satisfy that, well, when I take the projection, they go back to my linear code. At this point, you can tell me, yes, okay, so fine, but that doesn't really describe what is the lattice, what does it look like. So I tried to do an explicit computation if you want to get a sense of how concretely you compute this stuff. So the concretely is that, so in my case, if you remember, I was looking at 3 copies of zeta, z of zeta 3. So that means that I'm actually looking at something of rank or dimension 6, so which explains that I have 6 rows here. Now, getting this explicit generator matrix is a little bit tricky because, so what you have to do is you have to take into account what I have explained to you in how you actually map the element of your ring of integer into your Euclidean space. And so this is actually what appears if you look at the structure of this matrix as these 2 by 2 blocks. So you have one here, you have one here, you have one here, then you have one here, and you have one here. Okay, so if we look at the structure of this matrix, and I'm going to do that on an example which I hope is more illuminating than in general, so you can do that in general. You can observe a few things. So we observe that this 1, 1, zeta 3 squared that appear many times, like, is actually the way you obtain your lattice, as I explained yesterday, like when you have just a z of zeta 3 and you want to obtain a 2-dimensional lattice out of it. Then you observe that actually here I have just 3 copies of this matrix, and this is actually not by chance. This is really related to what I have explained also yesterday in terms of relating the generator matrix of the linear code with the generator matrix of the lattice. So having 3 copies here is really happening because when you look at the repetition code, well, the generator matrix in systematic form is just 1, 1, 1. So what you actually have on the upper side of your matrix is actually just a tensor, or rather, yeah, it's a tensor of this matrix that creates the lattice in R2 from the ring of integer with the generator matrix of your code. And what you have at the bottom is actually the equivalent of what I defined yesterday as being, so I said, okay, I'm going to repeat that. In the normal, well, in the simple case over Z, you actually get the following thing. So what you see here is that actually, if you notice the blocks that I have here, I have actually 1 minus zeta 3 that appears and its conjugate. So the 2 blocks that I have below are actually the embedding of the ideal generated by 1 minus zeta 3, which is the generalization of this part of the generator matrix of the lattice. So if we look at the overall things we get, so imagine that now you want to check that this generator matrix does give us what we want. So that means you will need to take a 6-dimensional vector and multiply it with this generator matrix G. So what you observe is that actually the first 2 columns, they are really reconstructing the element in your ring of integer, which correspond to the lattice in R2. The same happens with column 3, 4, and 5, 6, but here there is also a multiple of your ideal which is added, which when you actually take the map by pi, namely you take the reduction modulo, well, this ideal, so this lattice are actually sent to 0. So if I denote by U some 6-dimensional vector that you use to create a lattice point out of this generator matrix, you can actually check that what you get is indeed the repetition code. Okay, so this example is not so much to give you really the proof, but more to show you what usually people don't really explicit, because they're usually most interested in the gram matrix, is how you actually construct things if you are interested in doing so. Okay, so now I have explained the way we did this construction A by replacing Z by some more general structure, so typically a ring of integer or an ideal or an order inside. I would like to make some remarks. So an important parameter of a lattice is its volume. So the volume, okay, it's often, so there are sometimes convention depending on the author. So sometimes it's considered as the determinant of the gram matrix. Sometimes there is the convention that you take the square root. So in this example, I have taken the convection of the square root. So it's a simple computation that, there should be really a determinant here. Okay, all right. And so you just get the gram matrix and you compute the determinant. You take the square root or not, depending on the convention that you use. So now, if you actually do that, okay, so I did find another typo. So if you actually do that with the construction here that I have explained from cyclotomic field, something which is actually interesting is that you can see that the volume that you obtain is a power of P. And actually the power of P that appears depends on the parameters. So N is actually the number of copy that you use. And M is actually the dimension of the code. And the reason for this formula is actually coming from, there are some number theoretic behind that I have put in parentheses for people who are familiar with that. So what's happening is basically when you compute the gram matrix, you end up, or the determinant of the gram matrix, you end up computing the discriminant of your number field, which is the key ingredient in deriving this formula. And this is actually useful because, again, as I said, when you want to characterize a lattice, being able to figure out its volume is actually a very important way to characterize the lattice. So this is one example that tells you how the parameter of the linear code actually influence the lattice that you are getting out of it. Now I would like to briefly go through a series of well-known correspondences. I will not give a proof, but I just want to list some of the properties which I think are interesting. So if you are looking at a lattice, you have a notion of dual lattice. So what is a dual lattice? So if you are given a lattice lambda, the dual lattice will be all the vectors in your ambient space whose inner product will give you something in Z, no matter which vector Y in lambda you pick to construct your inner product. So a particular interesting, so the notion of dual lattice is useful for people who are interested in structured lattices or in characterizing lattices. In a sense, it characterizes, well, very structured lattice. So in particular, if lambda is equal to its dual, the lattice is said to be unimodular. And it gives rise to a number of exceptional lattices. You can also replace the notion of unimodular with other notion of modularity, like p-modularity, or there are other definitions that you can generalize, which can also be defined as a function of the lattice and its dual. And of course, if you have been studying codes, you know that there is a notion of duality as well for a linear code. So for a linear code, the dual is defined in that manner. So you also look at all vector in your ambient space such that the inner product will be 0 for any vector in your code. So in a sense, you can see that, I don't know, the two definitions maybe have some level of similarity. In both cases, you are looking at every vector in the ambient space. And in both cases, they satisfy a condition with respect to the inner product of any vectors in either the code or the lattice. Just for the lattice, you want the inner product to be an integer, and for the dual code, you want it to be 0. And so for equality between the lattice and its dual, I said it's unimodular. For a code and its dual, it's actually self-duality. Okay, so one interesting fact that comes from construction A is you may be wondering, okay, am I able to connect a duality in the code with duality in the lattice? And the answer is yes. So you can actually prove an interesting result for this construction, which is that there is an argument that always tie up the lattice. So the argument that I have written here says that if you have, you take a code and it's dual, and you construct a corresponding lattice using construction A, it will be always included into taking the lattice by construction A, and you take its dual. So in a sense, there is something that always, so there is a strong connection between being a dual, the dual of the code and the dual of the lattice. And in this particular construction using cyclotomic fields, so what you can also prove is that if you, so from the moment you have this relationship, if you have, you can use a volume argument to actually prove the following equality. And so you get a result that under a suitable construction, so you need to build your number field to have a suitable volume, so a suitable discriminant if you want, under which condition you can prove that if your code is self-dual, then your lattice is actually unimodular. So this is actually quite a powerful relationship between the property, the structure of the self-dual, sorry, the structure of the code and the structure of the lattice. And it's a tool that has been quite useful for people who are interested in lattices to be able to find very structured lattices. Okay, so let me summarize some of the key points that I have mentioned about this. So what we have been doing in this part of the talk is that I've shown you that actually you can, instead of going from Z to FP, you can actually pick some suitable, either more general structure. And you can actually define in a similar manner a construction A. You can use your knowledge of number theory because the gram matrix will be related to the trace of element in this algebraic structure. You know what is the rank of the lattice you will find. You know what is the volume as a function of the dimension of your code, and you can prove in that particular case that a self-dual code gives you a unimodular lattice. And something also which is quite interesting, but I haven't put in this slide because, well, I guess we can never put all the interesting stuff. There is also an interesting connection that I'd like just to mention if you're interested between the weight enumerator of the code and the theta series, so theta series of the lattice. So the weight of enumerator, well, of the code is, so it's like, it's when you are looking at a polynomial that characterizes the number of code words that you have for each possible Hamming weight in your code. The theta series of the lattice is actually also a formal series whose coefficient count the number of lattice points that you have at different norm in your lattice. Some small observation about this. You may want to normalize or not. So when you look in the literature, whether you have a normalization or not depends a little bit on the nature of your construction A. An interesting, one of the stuff that I like with this construction is that when you put P is equal to 2, you actually get back the construction over Z. So in a sense, if you want, you can prove everything about Z of zeta P, and that will give you for free all the proof for the simple construction A over Z. And I'm going to list some of the application of this type of construction, and it's not exhaustive and it's not probably very precise, but just to give you a feel. One interesting application, which was probably one of the reasons why this whole thing got started. So there are some early paper by Forney on this construction, and they were actually interested from a more system viewpoint, let's say. So the idea is that, okay, so if you're a communication engineer and you have to send lattice points, somehow you need to find a way to label those lattice points, meaning you need to attach the strings of bits you are actually trying to transmit. You need to attach that to your lattice point. If we draw a small example with like 5 points in 2D, it looks like it's not so hard, but actually in high dimension with a number of points, it's really hard. Usually you can choose between making a lookup table with an exhaustive mapping, which is actually memory consuming, not very efficient, or you can try to find a labeling algorithm, which is also difficult. So what construction A gives you is that, well, if you do it with Z, it gives you an easy algorithm to label Zn, then it gives you a linear code that you know how to encode. So that was one motivation. Another motivation was for people who actually cared about lattices. So because actually, how do you find a good lattice even? Like you want to know, does there exist a lattice with a given set of properties? So being able to inherit the property of the code and to bring it to the lattice was actually used to get interesting lattices, meaning extremal lattices, meaning lattices whose shortest vector is large, dense lattices. And there has actually been quite a number of work done by mathematicians who were interested in modular form. The reason for that is the connection that I had mentioned, namely that the theta series of the lattice. Okay, so you can look at it as being a modular form, then you have the weighted numerator of your code, and you can connect both. So this was quite of interest for people who are interested in this type of mathematics. Another application for maybe more among the engineers or maybe more recent, okay, is this notion of physical network coding. So so I'll just put that in passing. If someone has interest, I can say a little bit more about it later. So now what I would like to actually give you as a concrete example actually is something quite different. I want to give you one example of interest coming from lattice-based cryptography. A problem which is called SIS, which is the short integer solution problem. So I'm going to explain to you what is the problem, and I will explain to you how it connects to the stuff I have been explaining so far. Then I will mention a couple of things people are interested, because I've been told that it would be good in this workshop to also not just give some basic, but also give some ideas of what people look at. And so in the research status, I'll probably say a few things about what I know people care about lattice-based crypto, and I will also mention briefly, if time permits, a few things I think can be interesting, in particular also from just a math viewpoint. Okay, so let me start by explaining what is the short integer solution. So I'm not an expert, so I hope I got most of the main things right about it. So the problem is like that. So I will try to phrase it a little bit like I've seen it written by computer scientists. So imagine you have an oracle, so a kind of a black box that outputs for you an n-dimensional random column vector A. It's chosen uniformly at random. Okay, so pay attention to this thing here. This vector A is usually assumed to live in ZQ, meaning the integer modulo Q. And just to be clear, Q doesn't have to be a prime. Okay, so these are not too bothered about this thing. So you can take so you get your random column vector. And so the oracle is there, and it gives you, whenever you ask, it gives you a vector at a time. And so after m calls, you can put all your n column vector together and gather a matrix which will have a coefficient modulo q, so n times m matrix. The short integer solution problem is the following thing. It's asking you, so given this random matrix that the oracle gave you, to find a vector z in an integer vector z such that az is equal to 0 with the constraint that the norm of the vector is small, so it's bounded by some parameter beta. Okay, so maybe let's look at this definition for a little while. So for me, at first I was a bit surprised with the mixture of alphabet or characteristic, which we don't see so often in the type of problem I'm looking at. So you are really looking for an integer vector z, so really something which is an integer. So when you look at it here, you are basically looking at your z modulo q. So you want that this integer vector z, when you look at it modulo q, it satisfies this property. So let's first make a few remarks about this problem. If there was no constraint on beta, this is really not a very interesting problem. You just want to find z, which is in the kernel of A. As I said, not very interesting. But what is interesting is that, yeah, so you don't want, so yes, so you are interested in finding this vector z, which is not trivial, but without the constraint on beta, you just solve for z, so nothing big going on here. However, we also need to be slightly cautious about the choice of beta itself. So if, say, you take beta, which is large, then you could imagine that something which is not the zero vector could be you actually take a vector that looks like that. So you put the whole zero vector, but you just put a q in there. So in doing that, your vector z is not zero. But yet it's really not interesting because as much as it is an integer vector, when you look at it modulo q, well, what will happen is just q becomes 0 and it's not interesting. So it's a somewhat trivial solution. So we don't want that to happen. The other observation is that somehow, again, a slightly different way of thinking than at least what I'm used to. The number n and m are not so important, but what we may notice is that actually, if you try to increase the number of columns that you have, what happens is if you can actually find a non-trivial solution with m column, you have no problem to find a non-trivial solution with more column because you just take the same solution and you just add zeros. So this is a sense to say that finally the value of n and m, like m, is not so critical in a sense. So it doesn't have to. You don't have to think of it as really a fixed value. And the other problem now is that, okay, so the other thing is that how do you even, so what we did is, okay, we started with saying we want to find a small vector z, which is why it's called a short integer solution. So it's integer because z is a vector of integer. It is short because you have a constraint on the norm of your vector. So what I've been telling you is that, yeah, so if b is too large, it's actually too easy. So we want to make beta small enough such that it's difficult. So the whole purpose is to try to find a problem which is difficult. But the tricky part is you don't want your problem to be too difficult because if it becomes too difficult, you may just not be able to solve it. So you want to find your parameter beta in such a way that you can actually find a solution. So to avoid the problem being too difficult, so you need to pick the parameters m, n, and q to guarantee the existence of a solution. The argument on how you are going to choose these parameters is actually an argument which is that I will explain here, which is based on the pigeonhole principle. So the idea is that, okay, so since you want a vector z which has small norms, so it's reasonable to think of trying to get a vector which has a bunch of 0 and 1. So what we do is we suppose that, okay, suppose there are more than q to the n vectors in this set. So this means you are looking at m-dimensional the vectors containing 0 and 1. So if there are more than q to the n vectors in here, that means we are forcing the following equality. So you want 2 to the m to be strictly more than q to the n. If you force the following thing, then you can apply the pigeonhole principle to notice that if you have two distinct vectors x and x prime, and they satisfy that when you apply A on them, you get the same result, because of the dimension of the matrix A and A prime, so they are n by n matrices. So because of the dimension of the matrices and the number of elements that we pick, so the constraint 2 to the m is more than q to the m. So it must be that ax is equal to ax prime. And therefore, well, if you rearrange this equation, you get that the difference x minus x prime is actually a solution of norm at most beta, as long as beta is greater or equal to square root of m. So this gives us a simple like counting argument to tell us that, well, if we pick beta, which is greater or equal to this quantity, so square root of n log 2 of q, so some order of magnitude, we are likely to be able to find a solution to this short integer solution problem. Okay, so what is it that we have done so far? So we have discussed a problem which say we want a problem which is somehow feasible, hard, but not too hard. So the idea is to use this problem as building block for building cryptographic protocol. Okay, so now this looks like it has zero relation whatsoever with what I have explained so far. So let me show you what is the relationship. So people who look at this field of lattice-based cryptography, they introduce this notion of what they call QRE lattices. So what is a QRE lattice? Well, it's a lattice, but it's defined in a different ways than how we usually like different than what I have explained. So the way I explained is I have given it in terms of a generator matrix. Here you can think of the analogy in terms of code. So when you have a linear code, you know that you can define your linear code. You can use either the generator matrix or you can use the parity check matrix. So if you want, you can think of the definition of QRE lattice as adopting the parity check viewpoint. So you are defining a lattice by saying that you are taking integer vectors z of integers such that az is equal to 0. So in a sense, you define the lattice with its parity check matrix if you wish. And well, what happens is that when you define your lattice in that manner, this particular lattice actually has the property that multiple, so QZM, so Q's multiple of the integer grid, if you want, they will live in this. This is simply due to the arithmetic because you are looking at this equality in ZQ. Okay, so what do we do that now? Well, it turns out that now, if you look at that as a lattice, solving the short integer solution problem is actually, you are looking for a short solution Z in this lattice. So you are actually you are being asked to find a short vector in this QRE lattice. So using this connection via what are called QRE lattice, you are basically taking a hard problem expressed in terms of integers, namely find a short solution, integer solution, to a hard problem on lattices, which is finding a short vector in your lattice, which is a problem which is known to be difficult. So to tie up the end of the connection, so here what I showed you is the connection between the short integer solution problem, the notion of lattices, but now I need to close the loop by just observing that when you actually build a lattice using construction A, well, the lattice obtained by construction A is actually a PRE lattice. Why? Because, well, you start with a linear code, so the whole zero vector will be in your code, so all the preimage of zero will be in there. So in particular, you will have the property that PZN is inside. So you get a PRE lattice, and I have shown here to make it easier to visualize the same example of a lattice we had seen earlier by construction A, where we can clearly also observe the property of it being a PRE lattice. Okay, so now how do we get from there? So one may be wondering if there are interesting construction A lattices for the short integer solution problem. And yeah, actually, for the reference, you have a similar construction that is called the learning with error problem, which has an exact type of formulation. So with the learning with error problem, you also start with solving a system of noisy equation, and then you show that it has connection to lattice. And so one may be wondering, so okay, for the SIS problem or the least learning with error problem, so are there interesting construction A? And well, this is a question which is actually really an open question. I have been discussing it with some research groups who are active on lattice-based cryptography, and they do believe that there are interesting things to be done in that direction. And they also do believe that you can do that with some of the algebraic construction, the type that I have been showing you, for example, using number field. Construction A exists on many algebraic structure. Again, I've shown you one that was using number field, just to give you a sense for those of you who are interested in more advanced topic. You can also, for example, have such construction on non-commutative algebra. So if you want to use more sophisticated tools, so just for, again, if you are interested in more advanced topics, so I'm giving you here an example. So what's happening is you can construct an example of a non-commutative algebra will be obtained by now, instead of taking just one number field, let's say here I call it L, you can actually take several of those. So for this particular construction, you do need not any number field. So the embedding I talked about earlier, they do need to have a group structure, and not only any group structure, they do need to have a cyclic group structure. So if you have a field extension, which is Galois, what you can do is you can actually construct a non-commutative algebra in that manner. So as a vector space, it's actually not complicated. You just have, if your extension has degree n, you just have n copies of your number field. And you fix a basis, which is some element E, that we call E, or that you can call whatever you want. All you need to know is the basis is formed by the different powers of E from 0 to E to the n. And E to the n, it must be an element that actually belongs to the ground field. So something that I should have written here. That's important. And it's actually defining a non-commutative algebra. So maybe I should specify that explicitly. And in your non-commutative algebra, what's happening? It means that actually when you multiply, so as a vector space structure, there is no complication. But when you want to define multiplication, it so happens that multiplication on the right and on the left are not the same. So when you want to commute an element of the number field with the generator E, you actually have to use the action of the Galois group on your element in order to be able to do that. But what makes this whole thing work is that actually it so happens that because you use a number field, you can create these cyclic algebras with any field extension, but because you use a number field, you again can find a Z basis inside. So you can basically end up this whole thing with a Z module structure, which then allow you to do a similar construction A. And I guess the reason why I'm showing that here is both my own bias, because I want to tell you a bit more about the kind of thing we can do with this type of algebra, but also because I've heard different people working on this topic of lattice-based crypto who told me that they think this kind of construction could be interesting. So for people who have interested in looking at this. So a side observation, and this is going to be, I guess, the moment where I will do also a few minutes of advertisement for the kind of work I've been interested in recently, is I'll also be wondering about, okay, so whether it may be for application to network coding or maybe for crypto, I've been wondering the following thing, whether there is a meaning to add a multiplicative structure to construction A. So lattices, of course, they are additive structures, but one may be wondering, given that they may come from an algebra structure, whether it's actually meaningful to even define that. And well, as I said, lattices are inherently additive, but the thing which is kind of nice with a construction A, when you do it over a number field or an algebra of your choice, well, they come with a natural multiplication. There is a little trick here, though, is that the natural multiplication tends to come on the algebra or the number field itself, not taking n copies of them. So now you may wonder the same thing, like could you do something like you just take your number field and you take a suitable ideal and you actually build your construction A exactly on the structure itself instead of taking several copies of it. And if you wanted to do that, one way what I thought would be a guiding principle on how to do that is I like the idea of retaining the nice duality property, by which I mean that you have a code, you have a lattice. By dual, I mean that if you know something about the dual of the code, you know something about the dual of the lattice, and so on and so forth. So the question would be, how do you even do that? Is it possible? And as a result, it is possible. And just to give you a flavor, and it's also to, as I said, a little bit, because I wanted to say something 5 minutes about some recent work, but also to give you an idea of the depth of this algebraic construction of lattices, is that actually those two I have explained earlier, as I showed you the construction just over the integers, and I show you the construction where you use zeta n instead of z of zeta n instead of z. And for both of these, so we had the same guiding principle. So namely, you had a map pi modulo some prime ideal in both cases. In both cases, you got alphabet, which were copies of finite fields, on which you could find a linear code. And then, in order to describe duality, you needed the notion of a trace form. When you do things over a more complicated object, the philosophy remains exactly the same. But of course, the objects become more complicated. So what we can actually show is that you can, instead of taking copies of z of zeta n, you can actually do that on some suitable ring of integers, where you, instead of having several copies, you really have a single copy. You still need to find a suitable ideal. And then what happened here is there is something, instead of getting different copies, you actually get as quotient some object, which is basically some polynomial ring. And this is actually nice because for people who are working on coding theory, you know there is a whole theory of understanding, for example, cyclic code from the viewpoint of polynomial ring. So from the moment you identify your quotient here as a polynomial ring, you can really identify suitable generators for your code in terms of generator polynomial, the same way you do it for the standard theory. And using this technique, you can actually get an interesting construction A type of lattices with a suitable choice form, algebraic, of course, and also retaining duality property, meaning that you can actually characterize unimodular lattices, for example. And you can actually push the abstraction further, where you can replace what you have been doing with your ring of integers by taking some suitable order in your algebra. again, the guiding principle is the same, only the object become a bit more complicated. So you need to define also a suitable ideal. So in here, I will typically pick something which is two-sided to avoid complication. But again, if you are familiar with more general ring structure or module structure, you can remove this hypothesis. And here, something also very interesting happens, which is that when you look at suitable quotient, what appear is not polynomial ring, but what are called skew polynomial ring. So these are polynomial ring where multiplication is non-commutative. And this is also connecting to some recent area of coding theory where people are interested of doing codes over non-commutative polynomials. So there is a whole theory about defining, for example, skew cyclic codes. And so this construction gives a nice connection to this theory of really coming from coding theory, linear code, but over skew polynomial codes. So this gives a variety of, again, algebraic structure, going from the most simple one, looking over the integer, to a fairly complicated one, a non-commutative algebra. I believe a number of interesting connection to different areas of coding theory and potential application. But again, the same, at the end of the day, underlying principle of being able of lifting a code, a linear code, to something which has a Z basis. Okay, so I guess I will conclude here by giving you some pointers for people who are interested in knowing more. So the book by Ebling, I think, is a very nice reference for mathematician. It explained very nicely connection between lattices and code, and mostly also whatever relate to the cyclotomic construction. You can find it's actually, I found it very nicely explained, and it has also deeper connection I skipped, for example, related to root lattices. For those of you who are also more interested in application to engineering, communication, communication system, crypto, I will do some advertisement for a book to which I contributed with many of my co-authors. It actually starts from scratch. I will take some of the things I have explained, but also really, as the title says, focus not only on the math, but also on the application. So depending on what are your interests, you can actually get quite a number of interesting information on how you use that actually for coding or for crypto, including some of the stuff to lattice-based, tied up to lattice-based crypto. For people who are interested in the non-commutative stuff, we have some work recently on that, where in particular, if you're interested in the approach to looking at skew polynomial codes or coding theory of a non-commutative polynomial ring. And for those of you who are interested in really the lattice-based crypto as such, there is this survey by Peikert, A Decade of Lattice Cryptography, where they will explain not only what I have shown you, the case of a short integer solution, but also the learning with error, the connection to crypto, and where he will actually also give you stuff that I skipped about complexity of this problem and how you can actually use this hard problem to build your crypto system. Okay, so I think that I've managed more or less to fit things on time. So I'll be happy to take any question if you have, and thank you for listening to me.
Yeah, thank you so much, Frederick, for this very nice talk. It's open for questions, as she said. So you can ask or type in the chat box. So while people think about questions, I just wanted to ask you. So you took this totally ramified ideal, and then you would get confused. And of course, if you were to take a general prime ideal, then you would get finite fields, not necessarily prime.
Yes.
Is it always preferable to take totally ramified primes like in that
No, I think you can really do it whichever way you want. The tricky part is that at the end of the day, you are typically interested. So as I said, one of the main one of the main interests is to be able to say something between the property of the code and the lattice, typically in terms of duality. So what happens in the case where it's totally ramified, in this particular case, also the case of cyclotomic field, you take a P prime, while you have ramification only in this prime P. So controlling the volume, namely the discriminant, is very easy.
Yeah.
So if you want to do that over something else, you can of course do it, but then you have to get interesting results, you actually need to control the discriminant. So, but it's actually of course possible. Yes.
The discriminant is related to the number field, right? Not the choice
Yes.
of type.
So so basically morally what's happening is once you fix your number field, you have the discriminant tells you the ramification.
Yes.
So the discriminant is really the volume of the lattice. So well, of course, if you use an ideal, it will influence because the norm of the ideal will contribute to the volume of the lattice. Yeah. So it's about being able to get the right ideal and the right discriminants so that you can use a volume argument to deduce modularity or p-modularity.
Okay. And where, I mean, I have a naive question. Where do the leech lattices and so on come in?
Yes, you can get leech lattices like that. So of course, there are two. So if you want to connect that to exceptional lattices, so you have two ways to look at it. So one is like you don't know yet. You are interested in knowing whether a particular lattice with some property exists, and so in which case you may use this construction by code to try to find it, or to have a systematic way to look for it. That's one approach. The other approach is you have a bunch of lattices you know exist, and you just want to know, does there exist a code that will give you this lattice? That's also another way to look at it. A third motivation actually for that would be you are interested in, again, you are studying lattices for their theta series because you are interested in the modular form viewpoint of it. So in this case, you may also be interested in this construction by code because, again, if you can, it's somehow easier to get the weight enumerator of your code than the theta series of your lattice. So then you can use this connection to get information about the theta series of your lattice.
Right. Okay, thank you. A lot of fascinating stuff. I see there is a comment by Chunai that it's...
Yes, there are crypto protocol. I see, are there any crypto protocol in this field or paper? Yes, so you can look at the survey by Packard. So you can find, for example, I guess one of the most, I would say, I guess, seminal work by now is the work by Regev. So he proposed a crypto system using I think it was the learning with error, which is following the similar, it's somehow a dual approach, a dual problem to the SIS problem I explained. So you can look at the paper, you will find a number of crypto protocols which are based on this problem I described.
More questions or comments? Yeah, so thank you so much, Frederick.
Oh, no worry.
Yeah, really. Of course, you're giving a third lecture tomorrow on a different topics.
Yeah, it will be very different. It will be very different topic.
I can say that even if people did not understand everything in the first two lectures, they may be able to follow the third lecture.
Yeah, it's pretty much completely unrelated. Yes, I mean, apart that there are codes involved, but that's about it.
Yeah, yes. Just to attract more people, in case somebody.
Excuse me, ma'am. Just out of the curiosity, I would like to ask that just by involving projection map, is there any other way to come from the linear codes to lattice?
So the thing is that if you, the philosophy behind is that when you look at linear code, typically they are defined over a finite field. Lattices, typically they are defined over something Euclidean space, something real complex. So how do you connect something real characteristic 0 with something finite like characteristic P. I guess this is really the most natural way. But that being said, you can also, I should have probably mentioned that. You can also refer to the book by Conway and Sloan, which is called Sphere Packings, Lattices and Group. And you will find in there a number of constructions. So this one is called construction A. You will find a construction B, C, and D. I think B, C, and D. Probably more. And in particular, so these are also ways of constructing lattices from linear codes. So all of those are actually. So they still involve going from one alphabet to another, but they are not strictly using the projection map. So that could maybe answer your question.
Oh, thank you very much.
Okay. Thanks, Frederick. Again, sorry about these technical problems in the beginning.
Actually, it was not so bad at all. It was solved within 10-15 minutes, so it's pretty good.
So we have therefore a short break now of about 10-11 minutes, and then we'll come back. I think we will try to start the subsequent lectures in time. Okay. So see you in just a bit. But I started already?
Hello?
Hi.
Can you hear me?
Yes, I can hear you.
Okay. Yes, so here I am.
I thought maybe you started already.
Oh, no. No. No, at 11, right?
Yeah.
No, yeah, I just shared to make sure that everything works.
Yeah, looks fine, yes.
So it's good to have these long breaks because, well, if something like this morning happens, then you can catch up.
Yeah, that was totally unexpected, I think.
Yeah.
No, I double checked with technical people. I think what this person was saying is not true. I mean, we definitely have our license copy of this domain.
Okay.
No, exclusively purchased actually for this conference.
Yeah, so I really insisted to use Zoom for my course because I think it's very good. But then at some point, the Zoom had security issues, and then TUE essentially said you shouldn't use it anymore. But then I was kind of lucky that I got the license anyways, paid for the entire year. So for teaching, not for exams, but for teaching, I continued using it anyways, and now they are fine with it. So luckily they renewed my license, and then I can still use it for this year.
Actually, for my own teaching in IIT Bombay, I'm using Zoom. So we have a license copy which allows 1,000 users.
Wow, that's a lot.
And in fact, I'm teaching this first year, Bachelor of Technology class. I have a total of about 700 students. Okay. So I have to use it. But then I insist that people register for the course. Especially young students, they can also sometimes do pranks. They can log in under different names and make some strange comments in chat box.
Oh yeah, well, if you have 700 people, it's not. Well, I'm not surprised that there is some.
So we try to find a way in which at least they cannot impersonate, and we have some moderators sitting in the audience.
That's very good. That's very good.
But I didn't want to get into that structure for this 1 week workshop. And,
no.
This institute, they were confident with Google Meet. Except one of our organizers, Arun himself, who's not feeling well today. So he's
I'm sorry. It's kind of crazy that when you reach all the people I know tell me that as soon as you reach 100 participants, there is always one or two at least weird people who who do stuff.
So I didn't understand. Sorry. Go ahead.
No, go ahead.
I was saying I didn't completely understand what was happening at 2 o'clock, but Masood seemed to suggest that he used his son's machine yesterday, and the person was probably belonged to the elementary school to which his son goes. And maybe some things automatically got recorded there or what. I think Elif helped us and Masood also to communicate with this guy in Turkish and resolve the problem. But anyway, I think you may have noticed we have already put up your slides on the workshop.
Yeah, sorry, I am a little behind, so I didn't check the website yet.
So I'm also saying this for the benefit of others who may be here.
Okay, okay, yeah.
The workshop website, now there is a new tab on the top, which is schedule or talks. And you click on that and you will see whatever lecture notes are currently available. Excuse me. Okay. Alberto, you're using Microsoft Surface Pro or iPad?
Yeah, it's a Surface Pro.
Yeah, okay, got so.
I like writing on the iPad as well, but the pen is much nicer, I think, on the Surface. So I don't know. I like because the tip of the pen moves a little bit, and then it's really like writing on paper.
Yeah.
The Apple Pencil is very rigid. I don't know. It's personal, probably.
Oh, yeah. They all have some good thing and some.
Oh, yeah.
Okay, I think it's time. So maybe you can start, Alberto. It's your
okay.
Second. Yeah, please.
Yeah. Okay. So welcome back to the lectures on rankometric codes, and I would like to start by reminding you a little bit what we were doing yesterday. So we were in section 4 of of our schedule, and remember that we were trying to construct MRD codes, and then we're kind of building a machinery to do that passes through vector, the so-called vector rankometric codes, or rankometric codes that are linear over an extension field. Okay, so and we want to construct those, and then from there move to matrix rankometric codes, and we kind of already have almost everything to do that, except for a good construction of vector rankometric codes with good rank properties. So, and the construction is going to be based on linearized polynomials, which I defined last time, polynomials of this form, and then we said that we were considering the linear space of linearized polynomials of degree up to S, and we could say things about this space. It's an FQ to the M linear space of dimension S plus 1, and the roots of a polynomial in lin S are an FQ linear space, and if P is not the zero polynomial, then the dimension over FQ of this linear space is upper bounded by the linearized degree of the polynomial. And then I stated the theorem I want to prove now, which is this. So D an integer between 1 and n, then there exists an FQ to the M linear space K, where the rank of any non-zero vector is at least D, and the dimension over FQ to the M of this space K is precisely n minus D plus 1. So before proving this theorem, I'm gonna state the corollary I care about, which is about matrix MRD code, which is very easy to prove then. So first we do that. So corollary is this. So let D again between 1 and n. Then there exists an MRD code. In MRD code C in, well, math, remember that's FQ n by m, okay, of rank distance precisely D. So how do we say this? Proof. Well, we take a basis, so take a basis gamma of the field extension, FQ to the M over FQ. Okay, and then K as in the theorem we are about to prove. Okay, and then the code C, which is I define it to be the image of my space K under gamma. So this has rank distance at least D. Sorry, yes. So so let me write rank distance exactly D. Yeah, well, a priori from the corollary, sorry, from the theorem, we know that this has rank distance at least D. Okay, and then the dimension of C over FQ, of course, that's equal to M n minus D plus 1. Okay, so in order to conclude the proof, we only need to show that the rank distance is actually D, and not just at least D, but that's a consequence of the singleton bound. So what we can write is that, well, M n minus D plus 1, so we know already that this is the dimension of C, but then we use the singleton bound, so this is no more than M n minus the rank distance of C plus 1, and then since the rank distance of C is at least D, okay, so I'm going to write the passages. So this is by the singleton bound, and this is because of this. There, this is no more than M n minus D plus 1, okay, and therefore this gives you that the rank distance of C is precisely D. Okay, so this concludes the proof of the corollary and gives you the MRD codes we were looking for. And so now we only have to prove the theorem. Well, only, okay? And we're going to use linearized polynomials to do that. Okay, any questions about this? So as we did yesterday, you just interrupt me if you have any questions, okay? So I'm going to write the proof of the theorem now. Okay, so I start by fixing a basis. Sorry, not a basis, but a set of n linearly independent elements in FQ to the M. Okay, so let E equal beta 1, beta n be an ordered set of FQ linearly independent elements of my big field FQ to the M, okay, and I can do this because by assumption n is no more than m. That's something I assumed at the very beginning of the lectures. Okay, then we're going to define an FQ to the M linear map using linearized polynomials. So we define in FQ to the M linear map, which I denote by E, V, and then E, so evaluation, and then it depends on the set E. So that's from the linearized polynomials of degree no more than n minus d, and then I go into FQ M to the power n, Okay, and my map is defined like this. So the evaluation of P of X is equal to, well, simply I evaluate the polynomial P at the points, betas. Okay, so P of beta 1, P beta n. Okay, and this is an element of fq to the m to the power n. Okay, and then I claim that the image of this map is a code, well, is a space K with the property I want. Okay, so I claim that K, which I define as the image of this, sorry, ln n minus t, okay, so has the desired property. Okay, so this is my claim, and now I will try to convince you that this is actually the case. Okay, well, first of all, it's essentially by definition that K is fq to the m linear, because it's just the well, it's the image of an fq to the m space under an fq to the m linear map. Okay, so K is fq to the m linear, and I write by linear algebra. Okay. Okay, and then the most important thing is about the rank of each vector if non-zero vector being lower bounded by d. Okay, so good. Let's take then a non-zero polynomial in the domain of the map. So take P of x in ln n minus d, and then I remove the zero polynomial. Okay. And then I let W, that's a subspace of fq to the m. It's the subspace generated by the entries of the evaluation. Okay, so W be the fq space generated by the entries of evaluation E P of x. So remember that the rank of a vector is precisely the dimension over fq of the space generated by its entries. Okay, so that's W is precisely what we want to study. Okay. So that we also observe that the polynomial induces, as it always does, okay, an fq linear evaluation map. Okay, so P of x induces an fq linear evaluation map which I denote by capital P. Okay, so little p is the polynomial, capital P is the corresponding evaluation map. Well, this map goes from the span of the betas, the span over fq, into fq to the m. Okay, so this is really the evaluation. You take an element in the span of the beta, you apply P to it, and you get an element of fq to the m. Okay, so the reason why we like this map is because the image of it is precisely W. Okay, so the image of P is W by definition. Okay, and then by the rank nullity theorem, I can say something about the dimension of W. So by the rank nullity theorem, what I have is that the dimension over fq of W is equal to n minus the dimension FQ of the space of the roots of the polynomial, and this is at least by the proposition we had yesterday, n minus, okay, the linearized degree of my polynomial p of x. Okay, but then I also know that this is because p of x is in lin n minus d, that's at least n minus d, which is precisely d. Okay, so therefore what we have shown that the rank of V is, which is precisely the dimension over FQ of the space W, is at least D for all non-zero elements of, for all non-zero polynomial, exactly. So for all, and therefore for all non-zero vectors in my space K. Okay, so therefore we have that rank of V is at least D for all V in K, V not zero. Okay, and then I also know from this that, well, since D is at least 1, that the evaluation map EV sub E is then injective. Okay, so in particular, this is really a consequence of this fact we just proved. So in particular, well, since D is at least 1, the map EV E is injective. And therefore, I know what the dimension over FQ to the M of K is. That's equal to dimension FQ to the M ln n minus d. And we know from, again, from the proposition part 1 that this is precisely n minus d plus 1. Okay, so that's again by the proposition we saw yesterday. Okay, so that's actually the end of the proof. Okay. Okay, so we are essentially done with the construction because, well, we have, so let's go back. So we have this theorem that tells us that there exists a space K in FQ to the M linear space K that has this nice property with respect to the vectors in it, okay, and the dimension. And then we already proved as a corollary that if such a space, capital K, exists, then I can construct an MRD code C, okay, of the distance I wanted. Okay, in particular, well, we have our MRD codes. And it's very interesting that, and I write it as a remark, that MRD codes then, they exist for all parameters that are compatible with the singleton type bound. And here there is like a big contrast with the theory of Hamming metric codes, if you are familiar with it, where so the Hamming metric analog of MRD codes, the MDS codes, they only exist over certain fields, okay, so over sufficiently large fields. Okay, so in the rank metric world, things are slightly different. And MRD codes, so the optimal ones, they actually exist for any set of parameters that is compatible with the singleton type bound. So that's something very nice about rank metric codes, and a big difference with their brothers, Hamming metric codes. So remark, MRD codes exist for all parameters that are admitted by the singleton type bound. For all parameters that are admitted by the singleton type bound. By the sort. Okay, very good. So any Any questions about this before I move on? Okay, so if you remember from yesterday, I said, well, we have this nice singleton type bound, and which gives us the definition of maximum rank distance code, MRD. And then I said there are always two natural questions when you have such a situation. Well, first of all is the existence question, which we just answered. MRD codes exist. And then the second question I had on my tablet was properties. Okay, so now that we know that MRD codes exist, so we're not talking about the empty set, we would like to know what their properties are. So what can we say about their structure, their parameters, their, well, any other properties you might think of. Okay, so...
Question, Albert?
Yeah.
No, so what do you mean by singleton type bound? Because MRD would mean that bound is an equality, right?
Exactly, yes. So I call the... So I call this the singleton bound singleton type bound.
Okay,
because sorry.
MRD, that means the rank distance is equal to that m into n minus
yeah
m plus 1, isn't it? So
yes.
So what are the constraints on the parameters? It looks to me that there are hardly any constraints other than whatever inequality you assume for m and n.
Oh, yeah. I mean, yeah. So I mean, So any parameters you can take. Yeah. I mean, the parameters, like, for example, I always take d in between like 1 and n, and n smaller than m. Yeah. So no, I'm not assuming. Yeah. So there are no particular constraints except for the natural ones that I...
Singleton doesn't impose any constraints, but the basic conditions, so to speak, do, I suppose.
Yeah. So n no more than m for the form of the singleton bound I have, but then you know it's not really necessary. That is not even necessary if you transpose, and then this is really what I mean. Admitted by the singleton type bound, and I can put it in quotes. Really all parameters, yes.
Sure.
Okay, good. So m.
Excuse me, Alberto.
Yeah.
But the codes that you construct here is linear, right?
Yeah.
But you
FQ linear.
FQ linear, yes. But this remark that you write here also for non-linear codes.
Well, if linear codes exist, then non-linear codes also exist, right? And we know that there are MRD codes that are not linear.
Okay, perfect. Thank you.
So, for example, of course, it's kind of cheating, but if you take an MRD code and then you translate it by a vector, that's not linear anymore already, but it's still MRD.
Okay, perfect.
Okay, it's fine. So, as I said, it's a little bit cheating. We know that there are, more substantially different examples. Okay, but yeah.
Okay.
But in my lectures, all codes are linear.
Thank you.
Okay, so as I said, now I would like to talk a little bit about the properties of MRD codes, and this takes me to the 5th chapter or section, however you want to call it, and the 5th chapter is duality, which is actually my favorite topic in coding theory. Okay, and I start with a definition. Okay, so the trace product between matrices X and Y in math is, so what I do, I denote it by X, xy in brackets, okay? And for me, that's equal to the trace of xy transpose. Okay, where, well, you certainly remember from linear algebra that the trace of a matrix is nothing else than the sum of its diagonal entries. Okay, and then I can do this because, this matrix is square. Okay. So this looks like a sophisticated definition, but it's actually very simple. Okay, so I put it as a note because it can actually help to understand things a little bit better. So the trace product of x and y, well, in order to compute it, you just have to sum over all ij, xij, and then yij. Okay, so for example, over the binary field F2, if I want to compute the product, the trace product between 1, 0, 0, 1, and then 1, 1, 1, 1, all what you have to do is to just, do the products of the entries of the matrix one by one and then sum them together, okay? So this is going to be 1 by 1 and then plus 0 by 1 and then again 0 by 1 and then another 1 by 1, and the sum is 0 over F2. Okay, so now that we know what the trace product of two matrices is, I can tell you what the dual of a code is, okay, which is the next definition. So the dual of C, so it's the collection of all the matrices that are trace orthogonal to all the matrices in a code. So I denote it by C perp. That's equal to the set of all the y in mat such that trace product between x and y is equal to 0 for all x in C. Okay, and then it essentially follows from the note that I had before and from basic linear algebra or elementary coding theory that the dimension of the dual code is precisely the dimension of the entire ambient space minus the dimension of the code. Okay, so I call it a proposition. So the dimension of the dual of C is equal to nm minus the dimension of the code itself. Okay, and then this follows from the note that I had before. Okay, so there are two main results in the duality theory of rank metric codes. So there are many actually results, okay? These are just kind of the two best known results of the duality theory of rank metric codes. So two main results in this area. So the first one are the so-called McWilliams type identity. Okay, and then they tell you that the rank distribution of C and C perp, they determine each other via very nice transformation. So the rank distribution of C and C perp determine each other. So I hope I have a little bit of time to tell you about this, but I'm not sure. I have a small presentation for this. And then second part is that, which is what I would like to tell you about now, is that the dual of an MRD code is MRD. Okay, and this is what I would like to explain now. So why is it true that the dual of an MRD code is automatically MRD? It doesn't matter how you got the MRD code. It could be via the construction that I just told you about, but it could be any other MRD code. Okay, so in particular, in the proof, you will see I'm not using in any way the specific construction of MRD code. In particular, I'm not using anything about linearized polynomials or vector rank metric codes. I'm not using anything of that. This is just true for any MRD code. Okay, and so in order to show you the proof of this, or at least the proof that I picked, I will need a concept. And I put it in a definition. So for a code C, any code, okay, so C in math and a subspace U of FQ to the N. So I define the U shortening of C. So I define it like that is C of U. So by definition, this is the set of all the matrices in the code whose column space is contained in U. Okay, and then it follows from the definitions that C of U is an FQ linear space. So note that C of U is FQ linear, and therefore is a subcode of the code I started with. Okay, so it's a rank metric code itself, but within the code I started from. Okay, so it's a subcode of C. Okay, and then in particular, you can also take as a code the entire ambient space. So we can take as C the entire ambient space, FQ n by m, and then C of U, which is FQ n by m U, right, which we often call mat U. Well, that's just the linear space of matrices whose column space is contained in U, all matrices. So then is the FQ space of matrices whose column space is contained in U. That's what it is. And I need to tell you something about this mat U thing before we can proceed, and that's a lemma for me. This we're going to need in the proof. Okay, so trust me for a second. So for U subspace of FQ to the N, we have the following. You can try this as an exercise, so I'm not proving the lemma. Okay, so first property is that the dimension of over FQ of mat U, this is equal to m times the dimension of U. And then second property is that we know exactly how the dual of mat U looks like. Okay, and that's very simple. So mat U dual, that's equal to mat U star. Okay, and where the star here, so this is the dual, is the standard dual in FQ to the N. Okay, so all the vectors that are orthogonal to all the vectors in U according to the standard product in there, standard inner product. Okay, and then the proof you can try as an exercise. So proof, so try as an exercise. This is really just linear algebra exercise. You don't need any coding theory for doing this. Okay, so then the result about the dual of an MRD code being MRD heavily uses the following proposition, which I proved myself, and it's actually very, very simple. it's just very useful for proving not just this result, but various other results of the duality theory of rank-metric codes. So let C be a code, okay, and U a subspace, and I call little u the dimension of U. All dimensions are over FQ from now on. And then what we have is the following. So you take C of U, so the subcode of all the matrices in C whose column spaces contain in U, and you want to compute its cardinality. And the cardinality is equal to the cardinality of the code. You have to divide by QM n minus little u, and then you multiply all of this by the cardinality of C perp U star. Okay. So, and I'm actually skipping the proof of this lemma, of this proposition. Okay. So I had planned to tell you about this. However, I really want to tell you something also about the McWilliams identities, and then I see it's already 11:35. So I'm going to skip the proof of this proposition and instead show you how to use this proposition to prove that the dual of an MRD code is MRD. Okay, so using the proposition, we can now show that the dual of an MRD code is MRD. Okay, and that's a theorem for us. Theorem. So not only the dual of an MRD is MRD, but we also know what the minimum distance is. So I give you the complete statement. So let's see in mat be MRD. Then C perp is MRD, and the rank distance of the perp is equal to n plus 2 minus the rank distance of C. Okay, so how to prove this? Well, trivial cases first. Okay, so if C is equal to the zero code or C is equal to mat, then we're good. Okay, so you just apply the definitions. Okay, we know exactly what the duals are. So the dual of the zero code is mat, and the dual of mat is the zero code. So there is really nothing to prove there. They are both MRDs by definition. Okay, so therefore we assume that the dimension of C is in between 1 and n minus 1. Therefore, assume dimension of C and m minus 1. And then I write simply D for the rank distance of C. Otherwise, it takes forever. Okay, so D for that, and also D perp for the rank distance of C perp. Okay, so we start from looking at what the singleton bound. So what is the singleton type bound for the dual code? Okay, because that's what we want to prove, right? We want to prove that the dual code meets the singleton type bound with equality. So let's first write down what the singleton type bound means for the dual code. So the singleton type bound for the perp of C reads mn minus m n minus d plus 1, which is the dimension of the dual code. Remember, the dimension of the dual code is mn minus the dimension of the code, right? But then we know that the code is MRD, so we know exactly what the dimension is. Smaller or equal than m n minus d perp plus 1. So that's the singleton bound for the dual of C. Okay, and this is actually equivalent, so it's really equivalent, it's not a consequence, it's just rewriting the bound. So that's d perp no more than n plus 2 minus d. Okay, so this is really the singleton type bound. It simplifies a lot, so in particular m goes away. And then what you have is that the dual code is MRD if and only if you have equality there. So therefore C perp is MRD if and only if D perp is equal to n plus 2 minus D, but that's also the same as D perp is at least n plus 2 minus D. Okay, just because you have this, right? So I'm writing this because the latter one is the easy to prove. Okay, so that's what we're gonna prove using the proposition that I showed you before. So we prove the latter. Okay, which is the same as proving that so C perp of U, the size of this is equal to 1. This means that the only matrix in C perp whose column space is contained in U is the 0 matrix. That's what it means. Okay, so for all U in FQ to the N with dimension of U equal to n minus d plus 1. Okay, so that's what we want to prove. Okay, so is it clear why this is the case? If this is not clear now, well, tell me. Otherwise, I continue with the proof. So the strategy is, while I rewrite the singleton bound in terms, well, as an inequality between d perp and d, and then meeting the singleton bound means that d perp is at least n plus 2 minus d. So, and this means that there is no matrix in the dual code of rank n plus 1 minus d. Okay, but this is the same as saying that there is no, so for all subspace of fq to the n of dimension n minus d plus 1, the only matrix in the dual code whose column space is contained in that space is precisely the 0 matrix, and there is nothing else. So that's the proof strategy. Okay. So now fix an arbitrary such U. So fix an arbitrary such U. And we apply the proposition. To the code C and the U star space, so the dual of U with respect to the standard inner product of fq to the n. Okay, and then if you do the passages, so obtaining, what you obtain is C U perp, sorry, U star, size of that is equal to size of C divided by Q M n minus D minus 1. And then here you have C perp U, just U, and that's because, so I write it like that. So here I'm using that. If you take U star and then you do star of that, you get U back. Okay, so that's, I'm using it here. Okay, and then I know that C has distance D. So we know that C has distance D. And the dimension of U perp, sorry, U star is equal to D minus 1. Right, because that's how dimensions behave in by taking the star in FQ to the n, right? So that's n minus n minus d plus 1. Okay. So that's what it is. So I know that C has distance d, and the dimension of U star is equal to d minus 1. And therefore, this equality that I wrote, I call it I. Okay, so I becomes one equal, C of U star. Okay, so we know that. And that's equal to then Q m n minus d plus 1, and the denominator is also m n minus d plus 1, and then C perp U. Okay, and then, well, I can delete these two, okay, and then I obtain that C perp of U is equal to 1 as well, okay. So C perp U is equal to 1, and that's precisely what I wanted to show. Okay, so remember, this is what we wanted to prove. Okay, so I call it maybe I. Yeah. Okay, so this concludes the proof. And so as I mentioned earlier, this is a purely combinatorial proof that does not care about where the code is coming from. You have a rank metric code and you know it's MRD. Maybe you construct it using linearized polynomials. Maybe you construct it in, well, I really don't know how, okay, but it doesn't matter, okay? The dual of that code you came up with, is another MRD code. Okay, so this is a very elegant result, I think, from the duality theory of MRD code. And the other very nice result I would like to tell you a little bit about to show another application of the proposition that I had before is, well, the McWilliams identities, okay? And for telling you about the McWilliams identities, since I have very big formulas there, I prepared a few slides, okay, which I'm gonna share now. So I'm gonna stop sharing the tablet, where OneNote at least. And then I will try now to share the, so let's see if I manage. So yeah, so my grandmother and I are approximately equally skilled when it comes to technology, but I think it's this one. Okay, so. Oh yeah. Okay, full screen. If I manage, good. Okay, so I think you see the presentation now. That's a very short presentation about the McWilliams identities, and I decided to prepare the slide just because it's, well, I have big formulas, as you will see, and I was afraid not to have enough time to write down everything. Okay, so let's start with that. Okay, so again, remember the rank distribution was defined at the very beginning of the lecture from yesterday as one of the main parameters or invariants of an error correcting code. So I remind you what the definition is. You have a code in FQ(n) by m and then an integer I. That wi rank of C is precisely the number of matrices in the code whose rank is equal to I. And then you call the tuple W0 up to Wn the rank distribution of the code. And And then the dual, that's something we just saw, or we saw the definition today. The dual of C is the set of all the matrices in the ambient space that are trace orthogonal to all the matrices in the code. Okay, so these are the McWilliams identities. So you don't have to pay too much attention to the formula to understand what they really tell you. Of course, the formula is important, and getting the formula is not trivial. So the result tells you that. So you take any code you like, and then you take an integer j between 0 and n. Then the jth element of the rank distribution of the dual code, so in other words, the number of rank j matrices in the dual code, can be written as an expression in the rank distribution of the primal code. Okay, the wi of C, where I ranges from 0 to n. Okay, so if you know, this result tells you that if you know the rank distribution of the code C, so how many matrices of each rank you have in the code, then you can compute the number of matrices of any rank you like in the dual code. And in the statement, you see these weird symbols in square brackets. So A, choose B, Q. This is simply the number of B-dimensional subspaces of an A-dimensional space over the finite field FQ. This number does not depend on the A-dimensional space you pick. You can take FQ to the A within FQ, and then a B-dimensional space in there, but any space of dimension A over FQ. Yeah, you get exactly the same formula. Okay, then the original proof that Delsart gave in 1971 uses association schemes, and in the next few slides I would like to show you a different proof that uses Möbius inversion and the proposition that I had in my on the tablet. Okay, and so this is a fundamental result in combinatorics, which you might want to remember also for the future. And that's a specialization of Möbius inversion, which is a result in order theory. And I specialize it for the poset of linear spaces. Okay, so this is a very classical result in combinatorics. And for the lattice of subspaces, it reads as follows. So I denote by calligraphic P of FQ to the n the set of all FQ subspaces of FQ to the n. Okay, all of them. And then I take f from this set into z be any function. I don't ask anything to this function. Okay, just any function you like. And then you define another function, which is g. Also, the domain is the p of fq to the n. And it's defined like this. So g of a space u. So you have to go through all the subspaces of u and then sum f of v. So f is a function that you already have, and then you construct this function g using f. Okay, so Möbius inversion tells you that if you are able to compute g, then you're also able to compute f, and it gives you a formula for that. So for any subspace u, okay, you have that f of u is equal. So you have to go through all the subspaces of U, just like before for computing G. And then you sum G of V, and you also multiply this by the mu of V and U. Mu V and U is the Möbius function of V and U. This has a general definition in combinatorics, but we have a closed simple formula for the lattice of subspaces. So in this setting, well, I can tell you exactly what mu of u is, and I can give you a formula for that. mu v u is equal to -1 to the power j minus 1, and then q to the binomial coefficient j minus I choose 2, where I is the dimension of v and j is the dimension of u. Okay, so any questions about Möbius inversion? So that's a technical result I'm going to use in the proof. You should really consider it as a standard, very standard tool in combinatorics. Okay, the short story is that you have functions f and g, and then g is defined by summing f, and then if you know g, how to compute g, explicitly, then you also know how to compute F. Okay, so now we can really prove the McWilliams identities by simply combining the proposition that we had in the notes and Möbius inversion. So for a code C in the subspace U, I define my functions f and g, and I put the code as a subscript because they depend on the code. So f of u is the number of matrices in the code whose column space is precisely u, and g of u is, well, I have to define it if I want to use Möbius inversion, the sum over all the v's in u f of v, and then that's really by definition, that's the number of matrices in the code whose column space is containing u, which is precisely the u shortening I had in the lecture notes. That's C of u. Okay, so now, again, by definition, the number of rank J matrices in the dual code, well, how do I compute this number? Well, one way of computing it, I sum over all the subspaces of fq to the n of dimension precisely j, and then the quantity I sum is f c perp of u, which is going to be the number of matrices in the dual code whose column space is precisely u. And since I'm summing over all the subspaces of dimension j, I get precisely the number of matrices of rank j in the dual code. Okay, so the sum I copy, and now I use Möbius inversion to express f in terms of g. Okay, and that's what it is. Okay, mu again is the Möbius function of the lattice of subspaces of fq to the n. Okay, and now, well, now I need, so let's look at it 1 second. So I have this expression, I have the g and I have the mu. Remember, the McWilliams identities are about connecting the code and the dual code. So I start from the dual code. Now I need to connect this to the original code I started from. Okay, and that's precisely where the proposition kicks in. Okay, because that relates the code and the dual code. Okay, so I just rewrote it. So this is really the CU C perp U star business that we had before. This is just stated for the dual code. Sorry, I wrote yesterday, but this is actually 10 minutes ago. Okay. Yes, so for the dual code C perp, and that's what it is. So the G of C perp of V is equal to, yeah, that expression. Okay, where V star is the orthogonal of V with respect to the standard inner product of fq to the n. Okay, so now we plug that in, and this is what we get. Okay, so the jth element of the rank distribution of the dual code is equal to, so here I plug in the formula for the Möbius function I have, and then this mj comes from this part, and then, well, and then I just write the other sums. Okay, and now we are essentially done because, well, there are like a few computations to make, and I will not bore you with that, but it's very standard now. Okay, so you just have to use some elementary properties of binomial coefficients with this subscript q, and yeah, if you just do the passages, you get precisely the McWilliams identities, McWilliams type identities by the chart I posted at the very beginning of the presentation. Yeah, so I have 2 minutes, and maybe I can mention one application of the McWilliams identities to enumerative combinatorics. Yes, so I'm going to start from a problem. This is currently an open problem in enumerative combinatorics. So if you have a profile, which is just a subset of entries of a certain matrix, okay, a set of positions, actually, more than entries, okay, and then you want to give a formula for the number of matrices over fq having a certain rank r and that are supported on this profile. This means that there are 0 outside the profile. So, for example, if you ask yourself what is the number of invertible n by n matrices over fq with 0 diagonal entries, then you're asking a question of the type stated in the problem. Okay, because your profile is all the positions except for the diagonal positions, And then you ask yourself how many matrices are there that are supported on the profile and have rank n, the maximum one. Okay, so this is an important open problem in enumerative combinatorics, and if you want to learn more about this, I strongly recommend this paper. Yeah, and it turns out that McWilliams identities can be used to solve some instances of this problem. So for example, using the McWilliams identities, you can compute the number of rank R matrices, actually any rank, not just the maximum rank, so that are 0 on the diagonal. Okay, so you can actually answer a generalized version of the problem of the question I posted before. And well, this is the formula you get. So the number of rank R matrices of size n by m over fq, and where all the diagonal entries of the form mii are 0 is given by, well, this monster number. And this is actually proved using the McWilliams identities, and you only have to well, describe things in the language of coding theory. So you call C of I the space of matrices that are supported on the diagonal entries. So all the matrices that only have something on the diagonal and they are 0 otherwise. And then, well, you observe that the C of I is a linear rank metric code. And also the quantity you want to compute, this nu R of I, is precisely the art element of the rank distribution of the dual of this code. Okay, so again, as I said, this is really just applying the definitions. So it's about observing things. And then, well, once you phrase the problem like this, then you have there the art element of the rank distribution of the dual of a code. And then you really feel the urge of applying the McWilliams identities there. You do that, and then, well, the code C of I is very simple. You know all the parameters, and yeah, if you do that, you really get this formula without essentially any effort. Okay, so that's the end of my presentation. It's 12:01 in Amsterdam. So sorry for being 1 minute late.
No problem. Thank you so much, Alberto. I guess it's open for questions or comments.
I have a question.
Mm-hmm. Hi.
So, is it interesting to consider multivariate versions of linearized polynomials? Have they been looked at in some context?
Yeah, that's certainly an interesting topic. Okay, so you want to essentially look at polynomials which are linearized in both variables, right? So you only have q to something powers both in x and y. Yeah, so they are certainly interesting objects. I'm not aware of any application of them in the context of coding theory, okay, or at least in the construction of rank metric codes, because for the construction of rank metric codes, the univariate are well, more than enough. Okay. Well, actually, yeah, it might be helpful to kind of introduce a second variable to describe like some maybe some of these polynomials in a different way, but I am not aware of any specific applications of these polynomials in coding theory.
Okay. And another related question: in the univariate setting, is there a nice notion of derivative for linearized polynomials? The usual notion will not be linearized, but
yeah. So there is a notion of not like derivative, but Q derivative, and there is a paper about that. And if you send me an email, I can look it up for you and then send it to you. And so where they derive a little bit the theory of Q derivatives of linearized polynomials, and then they use them to kind of prove the Q analog of the plus identities for vector rank metric codes.
Mm-hmm.
Oh, nice.
Okay. So there is a notion of that, and the theory gets, it's a lot more messy than in the Hamming case. But yes, people looked at that.
I see. Thank you.
You're welcome.
I just want to make a comment. The formula, it's very interesting what you wrote down with this rank profile and getting it from the McWilliams identities. As it turns out, we have also stumbled on a similar formula in a different context. I don't know if you've seen that. Peter Beelan, I think he's also here in the audience. Peter Beelan and I wrote a paper on what are called determinantal codes.
I think I saw that. Yeah.
In fact, we had worked out this formula, and then later on we saw what Delsart did and also what you did. So we have actually referred to that. I just wanted to mention that that kind of a thing arises in a different context, and we gave a totally different proof in this paper.
Okay, well, that's very interesting. It's kind of like, I was completely new to these questions, and I was just, reading papers because I like combinatorics. So sometimes I see on the archive a title that I like, and then I go like, well, let's see what's in this paper. And then, I like counting problems very much. And then I saw this formula and I thought, well, this is matrices in the end. So is there a coding theory interpretation of this? And so it was really a coincidence that I found out about this problem. But yes, so I actually talked to the people I mentioned, in particular, Alejandro Morales and Lewis. And this problem of counting matrices with given rank and restricted profile actually shows up in many areas of mathematics and even physics. So even in quantum field theory, there are problems that are closely connected to counting matrices with a given rank and profile. And
I see.
So it seems to be a very I don't know if you can say in English pervasive, but I think you see what I mean, like pervasive problem. So very interesting that you also.
So we were interested in the number of matrices of a fixed size with a given rank for which the sort of partial trace is non-zero or zero.
Oh, I see. So you sum the entries up to a certain.
And because that's exactly related to the weights of the
Oh, I see. So so if you.
It's related to the weight distribution of the determinantal codes.
I see. Yeah.
But that goes back to an older paper of Beelan, myself, and Satlaj, who is also one of the organizers. And
I see.
Discrete math.
Yeah. So you use the I trace, the so-called I trace. So you sum up to entry I.
Yeah.
Mm-hmm.
Alberto, may I ask a question?
Of course, yeah.
Thank you. Thanks for the last talk. Me, as a lecture speaker, also have been working on rank-metric codes with my students. And in your lecture, I noticed this. It's a really nice result about the duality of MRD codes. And we know that for Gabellinian codes, it's a dual code. It's still a Gabellinian code, in its representation, right?
Yeah.
And I guess you also are aware of many new MRD code constructions in recent years. And I wonder, what do you think about whether it's possible to write an explicit representations of the duals of some of these new MRD code constructions, which has similar representation as Gabellinian codes? Do you think it's possible?
Well, I don't know if it is possible or not, but I would be I think any contribution towards construction in the realm of rank metric codes should be, highly appreciated, because there are several problems that are connected to the theory of rank metric codes, and I think so not just problems, but even theories that could be developed using rank metric codes. And the reason why all these theories are still in their infancy is because we don't have enough examples of rank metric codes. So think about, for example, code-based cryptography.
Yeah.
So there are many proposals of code-based crypto systems based on codes for the Hamming metric, and the NIST actually encouraged the study of rank metric codes for application in code-based cryptography, but we essentially only have 3 constructions of codes.
Yeah, I agree with you. Yeah, and also, I'm interested in rank metric code. Also, it's partly because so there are not so many applications of rank metric codes in cryptography, and there are not so many rank metric codes that can be efficiently decodable.
Yeah, of course, like. So I think it's because, especially in the beginning, people were like, okay, so we have. So I think in the very beginning, nobody really looked into the problem of constructions because we had the Gabidulin codes and they were optimal, and the very first application that was considered was network coding. Okay, and then people were like, okay, so we already have optimal codes. We know how to decode them. Who cares about the rest, right? But then people were not, looking far enough, and then at other applications. So I'm thinking, for example, rank metric codes with other properties that could be used in networks, for example. For right now, for example, I'm working on codes that can be used to defeat adversaries in networks, and so we really see that we don't have enough examples to look at.
Yeah, I agree with you. Yeah.
Mm-hmm. Yeah, so I think any contribution about explicit descriptions of codes we know already, or even new ideas for, and you just have to hope, that you find a reviewer who is open enough to say, okay, so these codes, maybe they don't have optimal size. However,
Yeah, I also consider the decoding of some rank metric codes, like for more decodable rank metric codes could be quite interesting. Like from perspective, it's their applications.
You mean the decoding in a more efficient way?
Yes, yeah. I mean, like to find some polynomial time decoding algorithms for new codes.
Okay, yeah. Well, the algorithm I know I know that Frank Danilo and Ralph Kotter, they had the first algorithm, and then they came up with a new one, with another one in the second paper they wrote.
Yeah.
I mean, you can try. Yeah, I don't really know if you can beat Frank, but maybe you can try, of course.
Yeah, it's not debating, right? It can be about the collaboration, right?
Yeah.
You were Frank. I said you were Frank.
I work with Frank, yes.
No. You were Frank in the sense you were...
Oh, yeah. Oh, I see. Yeah. Yeah.
Just
I don't know. I'm also not really a decoder as a person. So I know decoding, and I came up with a couple of decoding algorithms for subspace codes, but so maybe I just don't know enough, to tell you, oh, this is feasible, this is not feasible. So I just know that extremely good people tried, and yeah. This is all I know. But I'm not probably the best person to ask to for decoding.
There's a comment by Rocky.
The comment.
Sorry, I have to open the chat now.
Or you can speak, Rocky.
That's interesting.
Can you hear me?
Yes.
Okay. I just want to make one comment that this multivariate linearized polynomial is this has been used to construct those rank analog of Reed-Muller codes. This is a recent work by Ogo and Couvrier, and there are 2 other authors. I don't remember.
Okay. So okay. So the rank metric, okay, and then you say over Galois extensions. Oh, so they're kind of doing the rank analog of.
Yes.
Okay. So
Yes.
I see.
Yeah.
I see. Well, then, of course, if you're doing the rank analog of Rittmuller codes, they come from multivariate polynomials,
Exactly.
and then probably that's really the right object to look at. Thanks, Raki, for this.
Okay. Yeah. Thank you. And it was a very nice talk. And the proof was actually, I haven't seen the proof that MRD, dual of MRD is MRD. This proof was very nice.
Thanks.
Yeah, may I say something?
Yeah.
Thank you for showing the connection between graph theory and algebra in the first lecture.
Oh, the very first. Yeah. Thanks for the comment.
Yeah, and I just want to know, are you aware of these lifted MRD codes since they're connected with the designs?
Yeah, so this is what was in Annalena's talk yesterday, right?
Yeah.
The lifting, like you take a rank metric code and then you put an identity in front, and then you have identity and then X, and X ranges over the code, right?
Yeah, so this has connections with the designs, particular type of designs.
Oh, yeah. So there is yes. So there is a whole research area which is subspace designs.
Yeah.
Okay, so that's about the Q analogs of traditional combinatorial designs.
Yeah.
Okay, so since you asked this question, I assume you are familiar with combinatorial designs, like the set theoretic designs.
Yeah, I work in symmetric design, so I asked the question.
Okay, good. And then, so there is like a whole theory of the Q analog of those, and this was already initiated I think decades ago even, but then people really struggled to find examples, and maybe the motivation was not too strong for investigating those objects. But then, in 2008, when the whole subspace codes business was introduced, this kind of revived that research area too. And, there are actually several papers now on subspace design, which are the Q analog of combinatorial designs, and their connection with the theory of subspace codes.
Mm-hmm.
And lifted rank metric codes are just one example of one very special class of subspace codes. So, and I think that the context of if you restrict to lifted rank metric codes, you're kind of losing a little bit of, you're not really looking at the problem from the right perspective, which is really from subspace codes as a general object.
So
I don't think you gain a lot by focusing on the lifted ones.
No, that will give a particular type of design, I think.
Oh, yeah. So, yes. So these are essentially so they certainly have a very nice properties from a design theory point of view, just like, MRD codes are have an extremely rigid combinatorial structure. So MDS codes, for example, they give you very nice designs in the classical setting, and the lifted, I would expect the lifted MRD codes to be kind of also rigid as MRD codes, MDS codes, sorry.
Mm-hmm.
In terms of design properties.
Thank you.
The MDS are connected to orthogonal lattice coherence things, right?
I have a question.
Yeah, good.
Hi.
Hello. Yeah, very nice talk. Thank you.
Thanks for coming.
I just wondered, do you have the proof you gave for the McWilliams identities? Can you copy it more or less for higher versions of it when you look at the rank distribution, not only of individual elements, but of subcodes of a certain dimension, like 2 or 3 and so?
Yeah. So you just do it the same way. Yeah. So you mean the McWilliams type identity for the generalized weights, essentially?
Yes, exactly. Yes.
Yeah. So you just do it in the exact same way. You just have to adjust the definitions of F and G.
Okay, thank you. Great.
Yeah. I think I don't know if we wrote down all the details, but we have this paper together with Immerburn and Giuseppe Cottardo, who is PhD student, and like maybe we only did the binomial moments of it, but then so we have a paper about zeta functions and rank metric codes. And, so I don't remember if in there we only we did both, like the binomial moments and the explicit version, but I don't remember whether we wrote both of them in the paper then or just the binomial moments.
Okay, thank you.
No worries, thanks.
Hi.
Hi.
Hi, sir. I also have a question. Maybe you already have answered in your talk, but I think I missed something.
No worries.
What can we say about number of MRD code by fixing the parameters? In the first talk by Professor Sudhir, we have seen that, he has discussed that there are lots of MDS codes when we talk about having metric. So what can we say about MRD codes? Number of MRD codes or some asymptotic formula or they are finite.
We can discuss about this problem for days because I have been it was kind of the main problem I worked on in the past 4 years. So one of the problems, so it is really interesting for me. And so I think that giving an exact formula for the number of MRD codes, just, as giving an exact formula for the number of MDS codes is extremely hard. Okay, and that's connected with the structure of certain geometric lattices that have been around since the 50s and 70s. And so essentially counting the number of codes with certain properties is equivalent to computing the Whitney numbers of certain geometric lattices. And this is kind of one of the major open problems in enumerative combinatorics. One of the main open problems. Okay, so this is very difficult. So on the other hand, you can get quite explicit results if you look at the asymptotics of the problem. So, for example, if you ask yourself what is the proportion of MDS codes of say minimum distance d, and therefore k equal to n minus d plus 1 within the set of all k-dimensional MDS codes. So number of k-dimensional MDS codes divided by number of k-dimensional codes as a whole. So just the binomial coefficient and choose kq. Okay. Well, then if you take this ratio and you consider it as a function of q and then you send q to infinity, you get 1. So most codes are MDS.
Yes.
So, and we just proved together with my student at TUE that in the rank metric setting, that's exactly the opposite. Okay, so if you fix a certain minimum distance and you take the corresponding k, and then you ask yourself, what is the proportion of MRD codes of dimension k within the set of all k-dimensional MRD codes? Well, then you send q to infinity and you get an extremely small number. So while there are actually 4 approaches to this problem, and that gives you kind of bounds. And together with my student Anina Krutza, we managed to actually give a bound that goes to 0 very quickly. Okay, so not only MRD codes are sparse, whereas MDS codes are dense, but they are very sparse. Okay, so they're really a tiny fraction of the total number of codes if the if you send the field size to infinity. So I think counting is hopeless, giving exact formulas unless very specific parameters maybe. But then the problem is actually challenging but solvable in its asymptotic version. So I hope this answers the question at least in part.
Yes. Okay. Thank you.
That's very interesting. So, in MDS codes, what happens is that you can relate it to the points of the Grassmannian in which all Fluker coordinates are non-zero, which is sort of an open object. In fact...
Exactly. So, I can relate to that. And,
With the MRD code. So
yeah. So
not an option.
yeah. So I see the argument, and I think when you write MDS codes precisely as you suggested, with the Plucker coordinates, that's so you can essentially describe the MDS codes as the non-zero of a polynomial, right? It's all the matrices. Well, a generator matrix defines an MRD code if and only if all its minors are full rank. Right, and then you put the identity in the front, that's for free, and then you put variables in all the other positions, and then you write down the product of the determinants, and then you want to find a non-zero of that polynomial, and the degree of that polynomial is bounded in Q. So if you divide it by Q, it goes to 0. And then by the Schwartz-Zippel lemma, you find a non-zero of that polynomial. So that's one way of proving that MDS codes are dense.
Yeah,
and which I think is the argument you have in mind, just phrased in the Plucker coordinates, I think, right?
Sure.
Okay.
But
so
you
this
also have a formula which is of the same degree as the degree in Q of the Gaussian binomial.
Okay. Yeah. And you can try to do exactly the same proof with the Schwartz-Zippel lemma for MRD codes, and you miserably fail. And the problem there is the degree of the polynomial.
Nice.
And then because we thought with Immer we could prove that they are dense exactly in the same way, and then we came up with this polynomial, and we couldn't prove that the degree was small enough to apply the Schwartz-Zippel lemma, and then that was essentially the start of the problem.
Nice.
So this is really a problem that I love. Yeah. But then in the end, the strategy that we found together with my student Anina uses instead bipartite graphs. So it's a graph theory approach to the problem.
Very interesting. See, are there more questions or comments? We've had a very good talk. Thank you so much, Alberto.
Well, thank you. I am very happy that I participated to this, and I hope people could follow at least a little bit. And
yes, I'm sure many people followed, and you have been kind enough to give us your slides, which we put up on the workshop page, so one can also look at it later, etc.
Yeah, so I'm gonna send you the updated version of the PDF, okay, of what I scribbled on the iPad, and then the 3 slides I have on the McWilliams identities.
Yeah. So thank you once again for your.
Thank you to everybody for attending.
Last lecture. So thank you.
Good. Bye. Thanks.
Bye. And I think we've had a good discussion, but then that means that very small break. In about 4 minutes.
Sorry for taking the time. I didn't realize it was that late.
So, okay, we'll just resume in 4 to 5 minutes with Chunlai. And maybe Sartaj will introduce him. Sartaj, are you there?
Yes, I'm here. I'm trying to share my screen.
Yeah, okay, great. Yeah, we have a few minutes, so I'm also going to get a glass of water or something.
Hello, Shunlai.
You want to try sharing your, you just want to see?
Yeah, so I'm trying to share my screen, but I see I need to set it up to allow this screen recording, or Google might, it mentions Google Chrome might not have a screen recording permission. So I guess I need to set up, and then I need to rejoin the.
Okay.
Yeah.
Okay. Yeah, so your slides are visible. Chula, you need to unmute yourself. You're trying to say something?
Saturday?
Yeah.
Can you hear me now?
Yeah, so your slides are visible.
Oh, my slide is visible. That's great.
Yeah.
Shall I start or?
It's not full screen.
It's not full screen. Okay.
No.
I haven't used a Google Meeting before.
Okay.
I mostly use Zoom.
Okay.
Zoom meeting for my lecture. Is it not full screen?
It will take some time. Just wait for a few seconds.
Mm-hmm.
I think it will come.
It came and went.
How about now?
No, it's
not yet.
It's not there. I think
it was seen for a fraction of a second, and then
I can stop sharing and re-share it again. Maybe that's a problem.
Okay.
Yeah. What about now?
Let's see. Yeah, it's coming.
Yeah, it's there now.
Okay, now
it's all right.
Everything's okay? Yeah?
Yeah.
Yes.
Yeah.
Okay, great.
So shall we wait for a while, or shall we?
Should I start, or should we wait for a few more minutes?
Maybe. Yeah, I'll just introduce you and then you may start.
Okay.
Okay, great. So, welcome back to the next talk. So, it's my pleasure
to introduce Professor Chulnai Lee from University of Bergen, Norway. Professor Chulnai Lee completed his bachelor's and master's degrees in mathematics and cryptography in Hubei University, Wuhan, China in 2005 and 2008. And during his master's program, he was focusing on design of cryptographically strong Boolean functions. And then he began his PhD program at the Selmas Center, Department of Informatics, University of Bergen. And he did his PhD with Professor Tor Halleseth in the area of applications of highly nonlinear functions in signal design and coding theory. And at present, he is associate professor there in the Department of Computer Science. With this brief introduction, I would request Professor Chulnai Lee to begin with his talk.
Okay, thank you very much, Sataji, for the nice introduction, and thank for the organizers to invite me to give this talk. It's been a great pleasure to be involved in this excellent workshop. I have prepared two lectures. One is about linear code from nonlinear functions. This is about Hamming metric in coding theory. And tomorrow I will give another talk. It's about rank metric codes. And it's like a continual of Alberto's talk. But tomorrow's talk, I will focus on the decoding algorithms and also the applications of rank metric codes. Okay, let's get started for today's talk. So this talk consists of 3 parts. In general, it's 2 parts. So the first part is about some constructions of linear codes. The reason I introduce this part because as I have worked on the linear code constructions for the last years, I see there are different kind of constructions, and it took me a while to figure out the relation between these constructions, although in the end it seems it's quite simple. And so I think it's necessary for students or people who are not quite familiar with the area to be aware of that. And after that, so I will also mention the weight enumerator of linear codes and some relation between the constructions, and also if the codes are constructed from nonlinear functions, then what's the relation between the weight enumerator of the codes and some properties of the functions used to construct the code. And the second part is about our recent work. So it's about some linear codes constructed from 2-to-1 mappings. This is a joint work with a visiting PhD student, Kangchen Li, in the last year in our summer center, and together with Tor Halleseth and his and Longjiang Qu, who is the PhD supervisor of Kangchen Li. And in the end, I would like to mention some open problems along this research line, and hopefully it will be interesting to some of you. So let's start with constructions of linear codes. So first of all, I'd like to kind of briefly mention some notations, although I consider it's every audience would be familiar with these notations, just to make it self-complete. So here we use fq to the m to denote the finite field with q to the m elements, and we use this trace function. It's from m and from fq to the m to its subfield fq to the k. And we will use the notation fq to the n to denote the n-dimensional vector space over fq. And then we can come to the linear codes. So a linear and nkd, this notation linear code
when we use this notation, we use it to denote a k-dimensional subspace of FQ to the n. And in this subspace, the minimum weight, here this weight is respect to the Hamming metric. The minimum weight of all code words in this subspace is d. And this minimum distance is important. It determines the error correcting ability of this code. Another important parameters of a linear code is this weight enumerator of the code. It's basically this. Normally it is written as a polynomial form, and also sometimes it's written in this the Machiavellian type with two variants. And here, these AIs, the coefficient of this polynomial is the number of the code words in this code with Hamming weight I. And this weight enumerator parameter is quite important for linear codes. Especially, it can be used to evaluate the performance of the code during the decoding process, and especially people can use this weight distribution, this coefficient AIs, to calculate the probability of error detecting the error detecting process. And also here we have this the dual code in Hamming metric. So it's normally it's just the inner product of. So we take any code word in C, and then for any code word in the dual, it's the inner product of these two code words would be 0. It means every code word in its dual would be orthogonal to the code words in the original code. These are the very brief instruction of some parameters and the notations of the linear codes. From here, we know that normally people are interested to find good codes. Then what do we mean by good codes, and what other codes are kind of interesting to researchers, to coding theorists, and to engineers? Well, it's like here, it's some kind of personal opinion on it. Normally, linear codes are considered quite interesting when they achieve some bounds, like the Hamming bound or Singleton bound or some other bounds on the parameters of the code. And some of the design of the linear codes might have close connections with other research topics in other ways, and it might be able to apply this code in some other areas like sequence design, or use it for cryptography usage, or it could have some close connection with some objects in combinatorial theory. And regarding the application aspect, so linear codes are quite interesting if in communication and in storage systems, especially for some codes, they achieve this the capacity of the channel. So for example, people are interested in constructing distance optimal codes or dimension optimal codes. These are respected to normally the Hamming bound. Sometimes it's also respected to the Singleton bound. And regarding the applications and the connections with other areas, people are interested in few weight codes. It means the linear codes is shown to have very few non-zero weights. In this case, when we try to determine the weight enumerator of this code, the problem is relatively easier. And also it has been found some applications of this type of codes in secret sharing schemes, also association schemes. And sometimes these schemes could have good this access structure. And for applications of of codes in communications, like especially for the wireless communications, mostly some code with the capacity achieving property is of most interest, like LTBC codes and the polar codes. So let's think about look at some constructions of linear codes. The first one is this generic construction. So we consider the codes as generated by a matrix. So it's a kind of a typical tutorial on classic coding theory course. Like if we can find generate a matrix with rank k, and then we can use this matrix to generate a code. Basically, we have k linearly independent vectors in fq to the n, and then we use them to generate a vector subspace. And then we get a linear code with dimension k. And in this case, this G, this matrix, sometimes it's given as the systematic form. Some of them, they are given as just the normal vector form, and they don't have a clear term or clear pattern in its representation. But these vectors are linearly independent to guarantee that the resulting code have a dimension k. This is one generic construction. And around 2006, 2007, Professor Chen Sending and Professor Literator, they proposed another construction they called the defining set construction. So in this case, so they choose a subset of a finite field here, fq to the m, and then they define a code based on this definition. So they take the element of this subset. Then for each of these elements, they calculate the trace, and here with this x ranging all the elements in the finite field fq to the m. So in this case, this code is uniquely defined by this defining set. And from its representation, it can be easily seen that this code has length n, that's a one parameter. And its dimension, since here x spans through all the possible elements in fq to the m, so it's at most, the dimension is at most m, but it could be less than m, depending on whether these elements d1, d2 till dn, these n elements are linearly independent or not. So we have these two generic constructions, and as I see it, for most of the construction of linear codes in the past, they rely on these two constructions. It will be natural to ask this question: what is the relation between these two constructions? So what's the relation between these two constructions? Well, in the beginning, I thought they are kind of, because from its representation, they are not quite related, or in some sense, they might be related, but what could be the essential relation? Well, but in fact, if we take a little bit closer look at this relation, it turns out they are essentially the same. So here is the logic behind it. Because if we have, like, from the construction 1, if we take the vectors g, let's say g equals g1 till executing, here is a type, it should be gk. So if we take the row vector of the matrix, then we have g1 and till gk. Then the construction 1 basically gives you, okay, if we choose the message x, and then we times this, time it by this here, sorry, excuse me, it's not a typer, it's considered as the columns of the matrix G. Then in this case, we have for the message x with length k, then for each of the column, then we get the code word coordinates. So basically, it's like a linear combination of the coordinates in GIs. Then in this way, we can use this trace function to dilute this inner product. So based on some coefficient lambda. And if we properly choose the basis of fq to the n over fq, then in this case, the lambda could be 1. Then we can write this code word, this CIs, basically as, okay, it's x times g. This is the original construction 1 from the generator matrix. Then in this case, for each column, each coordinate of this CI, then we have the first coordinate is represented as a trace form, and all the coordinates in the code word then can be represented as a trace function of x times this gi. Then you see here it's we have this code word representation, and from here you see the construction 2. We choose n vectors in fq to the m, and then we have these trace functions of these coordinates, and they are basically the same. Here we have g1 to gn. So therefore, these two constructions are essentially the same. And now based on this observation, we can take a look at some constructions of codes from nonlinear functions. These are the typical constructions of linear codes such that the property of the resulting codes can be analyzed based on the properties of the functions. So one widely used construction of linear codes in the literature is if we take a function f from fq to the m to fq to the m, then we take this code word in this form. So it's ax times plus b times fx. Then we let x here to run through all the possible elements in fq to the m. In this case, the code would have length q to the, sorry, here it should be q to the m. This notation should be q to the m. And q to the m. And the dimension here, because we have x and fx, mostly the dimension would be 2 times m, but sometimes if for the fx, suppose fx is just a linear function, then here it could be just m. So in general, the dimension of this type of code would be between m and 2 times m. And also, if this function here is, again, it's a typo, sorry about that. So if this function vanishes at a 0 point, then in here, then we have x0, and no matter what the value of a and b, and the value of this coordinate will be always 0. Then in this sense, it's not necessary to add this coordinate. So normally it is excluded. Then in this sense, the length of the code will be q to the power m minus 1. So based on these constructions, there are enormous good linear codes have been constructed in the past 20 years. And some of these codes are constructed based on planar functions, also termed perfect nonlinear functions. And some of the codes are constructed based on almost perfect nonlinear functions, that's APN functions. And some of them are constructed based on quadratic functions or some other functions. There are a lot of different construction of this type of construction from different functions. And for example, for the applications of this type of constructions of the code can be used for secret sharing scheme. So back to 2005, Professor Khaled, Ding, and Yuan proposed this kind of initiate this type of research line.
And I just checked this paper. It has received more than 200 citations. It means that this type of work has kind of triggered quite a lot of research in the community. So based on these constructions, let's relook at it and let's express its construction from the previous two constructions, and then we can find some relation of them based on this example. So first, this if we write this construction in the language of the generic construction 1 based on the generator matrix. In fact, here, if we have the function f here, then we can write, okay, for x, then in fq to the m, then we write f of x, it's a value corresponding to this f. And if we represent it here it's an element, x and f of x are elements in fq to the m. If we represent them in vectorial form, then it will be like, this will be like m rows, and here it will be m rows, so we have 2 m rows. Then these things, x here and fx here, they are not necessarily linear independent, so we are not 100% sure whether this generator matrix have rank 2 times m or it has rank smaller than 2 times m. But you see this form, it's like a generator matrix. And then we have the coefficient a and b, so you can consider them as the message. So we have this message, then multiply this by this generator matrix. So for the expression in construction 2, then in this case, we can define, based on this f of x, then we can define a subset in this way. So basically, it's like it has 2 coordinates in fq to the m. Then we have for the first coordinate is x, the second one is f of x, and we write it as a subset of fq to the m to the 2. And in this case, we can write all these elements as some element in fq to the m, so it's d1 till dn. Suppose here, in fact, if we let x run through fq to the m, here n would be q to the m. If fx is 0, then here n would be q to the m minus 1. Then in this case, for the original this construction, trace of a times x plus b times f of x in this form, then we can write like since x and fx can be written as di's. And here a and b, if we treat it as an element in fq to the m, that's a c. And so as a and b runs through fq to the m, then we have c runs through the finite field fq to the 2m's. Then in this case, we can write this term in this way. Sorry, here it should be 2 times m on the shoulder of the trace function. Then you see this construction of the code from functions can be written in these 2 terms. So from the previous this construction, then what are the relations, and like in which cases we use construction 1 and in which cases we consider construction 2 when we are looking for some good linear codes? Or since they are quite generic and they are essentially the same, so they have their own advantage and or benefit, if I allowed to say, and their disadvantages. So from construction 1, it gives you a clear information about the dimension of the code, because we choose a generator matrix with the rank k that's fixed. Then in this case, we have a clear information about the dimension and the length, but it's not clear how the medium distance of this type of codes. And in general, it's not easy to construct a matrix, and then we can get the code directly from the matrix. There are some examples, but they are relatively rare. And for the construction 2, because it uses this defining set, it can be connected to some other objects in other areas. Like for in the beginning, this defining set are considered as like maybe to chosen as defining different sets in combinatorics. And then later, some researchers proposed to define these sets as the image of some functions or as a pre-image of some functions for some values. So there are different ways. And in general, it's quite flexible because we don't have any restriction on the defining sets here. And so hopefully it also leads to a flexible code length, since the set size is not fixed. But it has a kind of disadvantage because it gives you very little information about the constructed codes. And for both of these constructions, it's generally infeasible to directly investigate the properties of the codes, or like to investigate the weight enumerators of the constructed codes. Then regarding this, let's look at the weight enumerators of some of these codes to see what are the relations here. So since these two constructions are the same, so we will look at construction 2. So let's say the defining set is this subset of length n. And we recall here the code word would be in this code, would be in this form. Each coordinate is a trace of the product of this b times di's. So when we consider the Hamming weight of this code word, we would like to know how many non-zero coordinates in its code word. Then the problem is normally converted to the other way around. So we consider how many of the coordinates in the code word is 0, and then we count these 0 coordinates. Then we subtract this the number of such coordinates from n. Then we get the the number of non-zero coordinates. So that's the Hamming weight. Why would we do this kind of conversion? Then here, based on this some character sum, like the Gaussian sum of some other exponential sums, then the cardinality of this set can be calculated based on this character sum. Here, for example, we want to calculate how many elements in this set. Basically, we want to know how many bi's in fq to the n gives this 0 when it's combined with di. Then in this case, we can let this if it's 0, then use the character sum. That we take y belongs to fq. Then in this case, we can consider the additive character of fq. And if it's 0, we know that it's always a contributor q. And if it's a non-zero here, we know that this sum would be 0. Then in this case, so we have the number of these coordinates being 0 would be this sum over q, because if it's 0, it will contribute to q. And if it's non-zero, then it will be 0. So then we can look at this sum. Here, because if we look at these possible y's, then if we choose y being 0, it will be always 0. So normally, then we will exclude this. We treated separately. So we look at y. If it's 0, then this part will be 1. Then we have n elements here. Then it contributed n. So we exclude that part. Then we only look at this y in the long for the long zero elements y in FQ. So in this case, the Hamming weight of the code word would be represented in this exponential form. And such exponential sum is generally difficult to calculate for Q larger than 2, especially for Q as power of prime. Because then it involves like the sum of the exponential sums, and it's not easy to determine. But it's relatively easier if Q here is 2. It means the code we are considering is binary code. Then in this case, we can convert it into then we can remove this part basically. So based on this operation, recently Professor Ding pointed out the connection of this type of linear codes with Boolean functions. So what's this relation? So let f be a Boolean function from f to the m to f2, and with the support like this. So it's basically all the values, all the x, such that f of x being 1. And in this case, if we define a defining set exactly as the support of a Boolean function, then the weight enumerator of this with this resulting code CDF would be connected to the wash transform of the Boolean function f. So here is the relation. So if we have this code word, and then from previous slide, we know it can be written in this form. Then here, if we look at it, then because Q is chosen as Q, then it can be reduced in this term. It's simpler. And since the n is the size of the defining set, so we have this df, and then we write that here from I to n. In fact, it's this di's can be seen as x, and here x is an element in the support of f.
Shulai, there is a question in the chat box.
Okay, sorry, I cannot. Yeah.
Yeah. So maybe I can read it out for you. So there is a question by Ritesh. So he says that, can you explain equation 3 at page 11 of the presentation?
Sorry?
Equation 3 at page 11.
Here?
Yeah.
Yes. Let me see the chart. I mean the last one, or is it the last one? Retest, right? Yes. I mean here you see, you mean from the second to the last equation, right? If I'm understanding correctly.
I think probably he's asking for equation 2, perhaps.
Yeah.
Ritesh, you can speak yourself.
Yeah. Okay. Yeah, I can just repeat a little bit. Okay. So here we are interested to count the number of i's such that if we have b here, then like for the number of I such that we have this value being 0, then in this case, so if it is 0, then we can consider to involve this part into an exponential sum. This exponential sum is based on the additive character of FQ. In this case, this character has the property that if we have this y running through of the
FQ, then if this is 0, this property of this additive character implies that if it is 0, it will give you the value Q. And if it is non-zero, then it will be always give you the value 0. So then here we want to count the number of the size of this set. Then we look at, okay, for each I, then whether this the value of this sum is Q or 0, right? I mean, here if it's 0, it will contribute Q. If it's non-zero, it will be 0. So it means that the sum of this, the value of these sums would be Q times of the size of this set. Then we have this representation or expression of the Hamming weight of CB. Is it clear? No?
Yes, sir.
Okay, yeah, great. And then we just take the 0 element from FQ out. Then we have this representation. Yeah. So from the previous expression of this Hamming weight, then since we are considering binary code, so we take Q as a 2. Then we have this reduced version of the expression. Then we do some extra here, like this DIs, in fact, is the element in the support of F. So we use it as this X from DF. It's just a different way to represent this term. But here, since we know that X belongs to DF, it means Fx will be 1. Then here here it's minus, then we add Fx here. We know that Fx is always 1 since X belongs to its support. So by doing this, then we change the sign of this sum from minus to plus. Okay, then continuing this expression, then because this df it's a support, then we can, if we consider the complement of this support, then it's the other part in that complement set. Fx will be always 0. This sum would be half of this sum, where here x runs through all the elements in F2 to the n, the whole field. If we look at this two, if you see if x belongs to df, the subset, then it is 1. If it is the element in its complement set, then it is 0. So it's 2 parts, and these 2 parts are the same. Then so it's this sum is a double of this sum. Then we have this, so 1/4 instead of 1/2 here. And also, but in this case, we need also consider whether this b is 0 or not. If b is 0, then it's slightly different from the in terms of this, like here, in terms of this trace of M1. If b is 0, it's always 0, then it needs to be taken care of. But in general, we can write in this form. So then, if for some of you are familiar with Boolean functions, and then you know that this is the wash transform of this Boolean function f of x. So, and at b, this point. So we write as the wash transform of f at b over 4. And for this part, if b is 0, then it will be 2 to the m, if the whole sum. If b is non-zero, then it will be 0. So then we have this indicator function, whether b is 0 or not. So in general, you see the Hamming weight of a code word CB can be expressed by its wash transform and the size of its support. So it means that if we can calculate the values of this wedge transform, we can get the Hamming weight of this code word. If we can get the value distribution of this one, then we can get the weight distribution of the code here. Here, by the value distribution and the code weight distribution, it means we count the number of, we count each of these values, the occurrence of these values. So how many times one value occurs in its spectrum. If we let this B runs through all the non-zero elements in FQ to the M. So this observation can be easily extended to FQ to the M. Here we look at it as FQ to the M. So B is FQ to the M. Since previously we mentioned the construction 2, and if we write this, if we have this construction of the code, and if we define a Boolean function, this GF as x fx, this is so this is the support of GF. Then in this case, we can write the weight of the code word in this function, in this code, in terms of the wedge transform of this function. So then from here, all in all, it tells you that if you want to determine the weight distribution or weight enumerator of this code from this function f, then you only need to look at its wedge transforms. And if you can determine the distribution of its wedge transforms, then you basically determine the weight enumerator of the code. That's the information you need to get. So here it's the transformation. Due to the time, I will skip this part. But it's just like to tell you the relation between the wedge transform of the Boolean function and the wedge transform of the function f here. To summarize, in the construction 1 and construction 2, so we note that these two constructions are the same. And if we want to find few weight linear codes that is constructed from Boolean functions, then basically we need to look at some Boolean functions with a few valued wedge transform. And in fact, there are extensive research efforts for seeking such Boolean functions. Then the next part is our recent work. It's kind of within the previous research line. We want to use some functions to construct linear codes with a few weights. There's a few weights like 3 weights or 5 weights. And this is a recent work. So in the constructions, we will look at 2-to-1 mappings of this such f. It means that for any element in its preimage fx, then it has exactly 2 preimages for any x. I mean, each value f of x has exactly 2 preimages. And this is the 2-to-1 mapping. And based on this 2-to-1 mapping, then first we can look at 2 Boolean functions. The first Boolean function is directly the image of x. So it means, we define a Boolean function f such that this Boolean function takes value 1 at all the image of fx. This is the first Boolean function. Then we also look at the second Boolean function, also from f of x. It's like look at the image of fx together with x. So then here, this is a subset of fq to the 2m,
when x runs through fq to the m. Then we consider this set as a support of a Boolean function g here. And then for weight enumerators of these two functions, as we have mentioned before, the weight enumerator would be uniquely determined by the Walsh spectrum of F and Walsh spectrum of G. Here's some relation of it. And so first for F, this Boolean function, if we consider its Walsh transform, it can be represented as the Walsh transform of the function f. Here, this f is fq to the m. The capital F is a function from fq to the m to itself. It is also determined. It is also defined with some Walsh transforms. And in this case, the Walsh transform of the Boolean function, this lowercase f at b, would be the Walsh transform of this capital F at 0b, but there's a factor in front of this Walsh transform. And for the Boolean function g, we would like to know the Walsh transform of this Boolean function g at a and b, these 2 points, this point. Then it turns out it also connects to the Walsh transform of the function f here. This f is a capital F from f to the m to itself. So here it means that the weight enumerator of the two codes, here we have mentioned CF and CG, in fact, has close connection with the Walsh transforms of this capital F. And how can we determine the Walsh transform this capital F? There's some extra relation, and in fact, we cannot randomly choose some functions, so some 2-to-1 mappings. That would be quite difficult. So we look at two categories. The first category is we call it generalized quadratic functions. The reason we choose this type of functions is because for quadratic functions, there's some well-known result. Then we can use this result to determine the value of its Walsh transform. And also there are some research on how to use these values and then find some other relation to determine the distribution of these values. So here is a well-known result. It basically tells you the possible values of the Walsh transform of a quadratic function. It is totally determined by its rank here. This rank is the dimension of this subset. You see here is we have the quadratic function, and then it's kind of a derivative of this quadratic function. Since it's the derivative of this quadratic function is linear, then we are considering the kernel of a linear space. And in the paper, we look at several a list of quadratic functions and its variants. By variant here, I mean the function itself is not necessarily in quadratic form. It could be in some other forms. But here, when we look at the Walsh transform, here, WF and A and B, we know that here for X, if we have a permutation operation on this X, it will not change the Walsh transform, the value of Walsh transform. So it means if we apply some inversion or some permutation transformation, we get the same result. So in this case, it allows extra flexibility to choose this F. Like for example, for the first one, it's not quadratic, but in fact, if we take x to the power d with d as the inverse of this, the inverse of this exponent, then it gives you the quadratic functions. So here are many of these such quadratic functions and their variants. So since here we have a long list, I will just look at one specific example to show you our logic and our idea in the work. So we have this function fx. Its original form is not quadratic, but if we take x to the power 2 times 2 to the m plus 1, like to take this exponent, and m is odd, then in this case m would be co-prime to this exponent would be co-prime to 2 to the power 2 times m plus 1. Then it's the size of the finite field. Then it means this operation is a permutation operation. Then it won't change the Wash transform values. Then in this case, we get f of x in this form. And you see it's the exponent all have like 2 weights. Then it's a quadratic form. Then if we look at the Wash transform of this function f at ab, it can be transformed into the Wash transform of f1. And here it's in fact it's not Wash transform because the y here is not linear anymore. It's a quadratic term. But all in all, this function is a quadratic function. If we can determine its rank, if the rank is small, then it gives us a hope that we could determine the value distribution of this Wash transform. So in this case, if we look at the linear form of its derivative, then we find, okay, this is the linearized polynomial with q degree 3. So in this case, we know that this linearized polynomial will have dimension either 3 or 1, because here the m is odd in this case. That's m is odd, and we also consider 2 times m plus 1. Then here it's due to this restriction, we know that this linearized polynomial can have either 8 solutions, or has 2 solutions, or have no solutions. Then from the previous this well-known fact, we know that this D is determined. It can be either n minus 1 or n minus 3. Then in this case, we can determine the possible values of this Wash transform. So you see here, it has this 5 possible values, and here is 2 to the power n is contributed from the point AB being 0. Then you always have this 2 to the n for any function f. Now here we have these 5 values. In many cases, if we have the 5 values Wash transform, it's quite difficult to calculate its value distribution, because it's quite difficult to find the extra equations to calculate it. And sometimes like people will stop, like we can say that, okay, it's a 5-valued distribution, but we don't find a way to calculate its distribution. But here, when we look at this AB, if we fix A as 0, then it corresponds to the code of the code CG. In this case, from the experimental result, we see that it has 3 possible values, not 5 possible values. When the Wash transform have 3 possible values, then we can use some identities to directly get the distribution. So this is what we like during work. Then in this case, we need to show that this function has exactly, this Wash transform has exactly 3 different values. How can we show that? In fact, we need to show that the kernel, when we replace A by 0, we get this linearized polynomials. Although here it is still the q degree 3, but we can show that this kernel has dimension. It can has dimension 3 only at when it's when this kernel has dimension 3, the Wash transform can be 0, and when it's not dimension 3, then it's the other case is dimension 1, then it has this value. So in this case, we basically prove that the value of this Wash transform at 0b for b runs through all elements, it gives you 3 value. Then we can solve it and we can determine the distribution of the code. Based on this, there are a lot of this type of 3-weight linear codes we have obtained. Another category is based on permutation polynomial. Due to the time limit, I will only briefly mention the idea behind it, and then I will describe our open problem along this research line. So in this case, we are still look at the 2-to-1 mappings. Then it's quite natural to ask, okay, why do you choose the corrective functions? Why don't you choose some other mappings? Then what's the special property of 2-to-1 mappings you really use? Well, in fact, we don't really use specific properties of 2-to-1 mappings. We only use the property that if you have the 2-to-1 mapping, then the size of image will be 2 to the n-1. So it's easier to handle. Then it's natural to think if I have a 2-to-1 mapping like x plus x2 times t, x to the power 2 to the t. This is, if t is 1 or like if t is any element, it's 1 ln. This is a 2-to-1 mapping. And also, if we choose an integer e coprime to 2 to the n-1, then this monomial x to the e is always a permutation. Then you may think, okay, if I have a permutation and I have a 2-to-1 mapping, then I can combine them. I can composite these 2 mappings. I will always get a 2-to-1 mappings. And that is true. So we have this category of the function. It is a composition of this 2-to-1 mapping together with this permutation. And it turns out that it's very interesting. We can calculate the Wash transform of this f here at 0b as a function p of x. Here p is a permutation polynomial, and in this case p is x to the power e. Then we can transform it to the permutation polynomial p at it's a Wash transform at b and 1. So then if here this p of x is properly chosen, then for some of the results we can get the Wash transform it, and then we can determine the possible values of this Wash transform. And in this case, if we choose e as some Lewin monomials with good properties, here there are a lot of there are abundance of research on choose this exponent e such that we can determine its Wash transform. And in this case, based on this construction, we can get the new codes with Lewin weight enumerators. So then we have this summary. Basically, it's like we use the 2-to-1 mapping to construct new linear codes with a new code length. And it's very natural to ask the questions whether it's possible to determine the weight enumerators or weight distributions of some linear codes constructed in this way. Especially even when it's a 5-weight, then what's a possible weight distribution of it? So that's an interesting problem. And another research problem would be if we don't choose 2-to-1 mappings, we choose T-to-1 mappings. Here T could be 3 or could be 4. Then what are the properties of the code? Can we find new good linear codes from this construction? Yeah, that's pretty much my talk and today. So sorry about the delay for 3 minutes.
Thank you, Chunlei, for your very nice talk.
Yeah, thanks.
Now the stage is open for the questions. Either you can ask directly or you can write in the chat box. Let me see the chat box. So there does not seem to be any question in the chat box. So it seems there is no question. Thank you very much, Chunlei, once again for your wonderful talk.
It's my pleasure. Yeah,
And
thanks.
We are looking forward for your next talk tomorrow.
Okay,
Thank you so much.
very much.
Yeah. So now
So then I will stop sharing. Yes. And
you can stop sharing now. Yeah. Okay. So
your slides to us, then we can.
Yeah, of course. Yeah, I will send my slide to you.
Very nice.
Okay. So now we'll be back again after 25 minutes. The next lecture is by Professor Peter Benin at 6:30. So we'll resume again at 6:30.
6:30 India time. So
Indian time, yes, 6:30 Indian time.
Wherever you are.
Okay. So.
Hi, Peter.
Hi.
So how do you do these things? You write on these whiteboards beforehand and then take images?
Yeah. That's
very novel.
It is faster than writing a beamer presentation.
Yeah.
But I mean, usually I would have done that, but since already had material, I went with it. Yes.
And you can share those images with us as some kind of...
if you want to, yeah.
Yeah, please. It will be nice, I think. So very systematically and...
Yeah, no, of course.
We have already started this tab on the workshop webpage of slides and talks.
Yeah, okay.
We'll put up a few things. And if you share with us, we'll be happy to add yours.
Yeah. Yeah, let's see. I don't know if I can just send it by email. Maybe I zipped.
No, but yeah, after your talk is fine. There's no... I mean...
Yeah, sure.
Yeah.
Just a second.
People are slowly returning from their break.
Yeah, sure.
We have about 3 minutes or so. Hi, Masud.
Hi, everyone.
Hi. So do you have students on the campus, or you actually come to? Do you have students on the campus who come to physical classes, or
no,
just
not at all.
Everything online?
Yeah.
But you go to the department occasionally or regularly?
If I must.
Okay.
Otherwise, it's all work from home.
Yeah.
No, it's pretty closed down here. But I guess it's the same for you, isn't it?
Yeah, it's pretty much the same. Of course, I do go once in a while, but yeah, mostly everything happens online, and I'm teaching. So yeah, I just work from home as much as most of the time, actually. Okay, so it is time. So if you like, you can just start slowly.
Okay.
Yeah, please.
Let me start by sharing the screen again. So yeah, welcome to my second lecture for this workshop. So I've been very interested in what other lectures, but unfortunately there are other obligations, so I missed out on a few. But I think it has been really interesting. So I'll try to add to the success by giving the second talk. And this time I'm really going to talk about decoding with Solomon codes. So let me share my screen. Yes. So if someone could tell me if you can see.
Yeah, we see a grid. We see a grid.
Yeah. Okay, so this is the first one from last time, so we'll skip ahead a bit, in fact. But maybe since this is a few days ago and there has been kind of a lot of information, let me just very quickly tell you again what the Reed-Solomon code is. So what it was all about is, given a finite field with q elements, you choose n distinct elements from this field and then evaluate polynomials up to a certain degree, strictly less than k, in those n evaluation points. So every polynomial gives rise to a code word, and then using the linearity and injectiveness of this evaluation map, when restricted to such polynomials, we get a code of length n, dimension k, and the minimum distance turned out to be n minus k plus 1. So they're actually MDS codes. So this is as good as it gets. The only drawback you could say is that the length of these codes is restricted. So the length is at most q, because there are no more elements from the finite field with q elements. If you take a slightly different point of view, you can get up to length q plus 1 by, so to say, thinking of fq as a line, and then a projective line would have an additional point to use as an evaluation point, so to say. But anyway, you can get up to length q plus 1 in this way if you want to. But in the usual setting, we say the length is at most q. So what we want to do is then to decode such codes. So what is decoding all about? So what it is really about is to recover the sent code word from the received words, and there are some assumptions made on the way, namely that the received word still has n coordinates, so we are not looking at insertions or deletions. That is a different game. But what we do have is n received code word symbols from the finite fields, and we want to recover the sent code word. I mean, what you ideally would like is that you just want to find a code word that is closest to R. So in general, there might be several such code words, but it would be fantastic if you simply could find, for any received word R, if you could find a closest code word. That is very ambitious. That's called maximum likelihood decoding. So then you can always find at least a very likely candidate for the code word back again. However, this is an extremely difficult problem. I mean, more precisely, it was already proved decades ago that if you want to do this for general linear codes, then there was an article by, let me think, Berlekamp and McLeese and Van Tilborg that showed that this is an NP-hard problem. Then more recently, you could still hope that maybe for Reed-Solomon codes you can do this, but more recently it was shown by Kugelswamy and Vardy that also for Reed-Solomon codes, maximum likelihood will be an NP-hard problem. So this question of finding always a closest code word, that is difficult, NP-hard in fact. But what you could do is be a bit less ambitious and say, well, let us assume something about the number of errors that have occurred. So if we assume this, so what does that actually mean? So what is the number of errors? So, well, if we have the sent code word C and the received word R, then the difference of the two is called the error vector, and the number of non-zero coordinates of the error vector tells you how many errors have occurred. So in other words, the Hamming weight of R minus C is the number of errors that have occurred. So the Hamming weight of R minus C is also the same as the Hamming distance between R and C. So in other words of looking at this is that the received word R cannot have drifted too far away from the sent code word C. So, so if we have this picture in mind, then the minimum distance comes in very nicely, because if we think of code word C as a kind of points on a lattice, so to say, but of course we're working over a finite field, but then we can imagine certain spheres of a radius around those code word C. And if you increase the radius, at some point these spheres are going to overlap, going to intersect each other. But since two code words are always at least d apart, minimum distance d, then as long as the radius of those spheres is strictly less than d half, there will be no overlap. So all these spheres will be disjoint from each other. And that means that maybe a less ambitious goal would be to try to correct up to d half errors. So strictly speaking, the minimum distance was n minus k plus 1. So we're going to assume that the number of errors is at most n minus k over 2, rounded down for convenience to get an integer. So this error correcting radius we're aiming for now is this tau, this n minus k over 2 rounded down. So then you can actually observe that given R, and given that at most this many errors have occurred, then the sent code word is the unique closest code word to R. So this also simplifies that problem. So, okay, so let us try to do that. So the goal today is to do this. And by the way, I should say that nothing that I'm really telling you is new. So decoding Reed-Solomon code is a well-studied topic. It has been for decades. And there are many different decoders around. They are somehow all related to each other. And it may well be I will say a little bit about that later on. So, okay, so one of the decoders that you might have heard that is quite classical is the Berlekamp-Massey decoder, but that has a completely different description. So if time allows, I'm also going to make some remarks about this. So the decoder I'm going to talk about is closer to the Sudan decoder and the Gao decoder of Reed-Solomon codes, just to put those names there. Okay, so what are we going to do? So let's introduce a little bit of notation that's going to be very convenient later on. And of course, if there are any questions, please tell me. When I'm sharing the screen, I cannot see the chat, so just speak up, or one of the organizers can tell me if there's a critical question in the chat on the way. Okay, so I want to introduce a set of error positions, and so what that is are all the coordinate positions I where the error vector has a non-zero coordinate. And well, in my mind, the set of error positions can also be thought of as the evaluation values xi where ei is non-zero. So in other words, it is also quite convenient to take these evaluation points themselves as index sets. And I identify these two things all the time. And when I looked through these slides again, I noticed that I'm doing this also here. So, but I'll tell you what's going on. But we have the set of error positions, and then we can also create a polynomial in the variable x that has exactly the xi as roots, where I are the error positions. And this is called the error locator. So knowing the error locator is already a big step on the way to being able to decode, because you see the problem with decoding is twofold. Sorry?
Yeah. So we don't see any board yet. Is that
Sorry?
No, we don't see any of the whiteboards yet. We just see several whiteboards. It's like a file folder.
Oh.
So, have you been meaning to show something? So then
Yes.
open that there.
So let me try again. Thank you for telling me.
Yeah.
Maybe if I just share my entire screen, if I can.
What we saw was you opened the folder, but then there were several files.
I see.
Several JPEG.
Just gonna show the entire screen. Then hopefully it can work out. What about now?
Yes, I think it is. Yeah, looks good.
Okay. Yes. Okay. So what I basically did is I ran through this first column here. So I repeated a bit about what a Reed-Solomon code is, and then introduced the notation script E for the set of error positions, and this lambda of x as the error locator that has all the xi as roots, where I indicates the error positions. So, okay. So let's try that again. So good you told me, because now there are going to be more formulas on the board here. So what I want to do is I want to give an intuitive idea of where the decoder I'm going to talk about comes from. This is not at all how it historically went, but I find this way a bit more convenient than others. So what is happening here is let us pretend we actually know everything. So we know the polynomial f that was used to create the code word, and we do know this error locator. So we know where the errors are. Oh yes, I now remember I want to say something. So decoding, really, you can think of it as two problems at the same time. It's not only that you have to find out what the error positions are, but also the error values. So somehow you don't know where the errors are. That would be a different game called erasure decoding. But for error correction, we don't know where the errors are. So we have to find out where they are and then which values this error vector has. So there's this twofold problem. So let us pretend we know everything and consider a bivariate polynomial, qx, y. So we have what does it look like? So I'm simply looking at this lambda of x, the error locator, times a very simple thing, y minus the polynomial f that was used to create the code word. So we can multiply this out if we wanted to and call the coefficient of y q1 and the coefficient of 1, the constant term, we call it q0 of x. So q1 and q0 are polynomials in x only. Now this polynomial has a nice property. So again, why look at this at all? So we're simply pretending to know everything and try to find a polynomial that has properties that actually are properties that the receiver could pose on a polynomial. So the receiver only knows R and the setup of the codes. He doesn't know anything about the number of errors or about the error vector. But nonetheless, we can try to study this polynomial. So let us cheat a bit here. So what does this polynomial satisfy? Well, it satisfies certain interpolation conditions. So more precisely, if I insert one of the evaluation points xi for the x variable and the ith coordinate of the received vector for the y coordinate, then I'm claiming this will always give you 0. And why is this? Well, there are two cases. Either we have an error in the ith position or we don't. So if we have an error in the ith position, then we know that x of I was a root of this polynomial lambda. So then it will be 0, the whole thing. If I is not an error position, then xi is not a root of this, but then the second part is going to be 0, because if no error occurred in the ith coordinates, Ri, the ith coordinate of the received word, is going to be the same as the ith coordinate of the sent code word, which was f of xi. So then the second part is going to be 0. So the netto effect is that this q of xi, ri is always 0. And that is a nice property because that is something the receiver could impose on a polynomial of this form, q1x times y plus q0x. Then there's a second condition which follows from the assumption now that at most tau errors occurred, where tau was the d-1 over 2. So n minus k over 2 in the case of Reed-Solomon codes. So what we know is that the degree of this error locator is then going to be at most the maximal number of errors we are allowing for now. So this tau. And the x degree of the constant term is going to be the degree of this error locator plus the degree of f. So for both we have an upper bound. The degree of this lambda x we assumed to be at most tau. The degree of the polynomial f is going to be at most k minus 1 by construction of the Reed-Solomon code. So we have these two upper bounds as well, and that is also something the receiver can impose. This has nothing to do with the precise structure of the errors, only that we use the assumption that at most n minus k over 2 errors have occurred. And then the third property that we see immediately is that actually the message polynomial f of x is minus q0 over q1. So we have that as well. And that is of course something that would be really nice. So the idea for the decoder here is the first version of the decoder is let us try to look at polynomials of this form q1x times y plus q0x that satisfy the first two requirements. And then hopefully the third requirement is going to be satisfied as well. So that's a leap of faith, but let us try. Let us try that. So that is the basic idea. And then usually this first, they are called the interpolation conditions, and the second, they are called the degree constraints. Okay, so let us try to do just that and see what happens. Okay, now the result is that if we try this, so if we are looking for polynomials, bivariate polynomials of this form that we just had, and assume that they satisfy the interpolation conditions and the degree constraints, then indeed it will be true that the used polynomial f is going to be minus q0 divided by q1. Now, of course, we want a non-zero solution to this. Otherwise, we cannot divide by 0 here. So any non-zero polynomial of the right form here that satisfies the interpolation conditions and the degree constraints can be used to recover the polynomial. And then either you can recover the message immediately by taking the coordinates of that polynomial, or if you insist on getting the code word itself, we can then evaluate this polynomial in all the xi, in evaluation points. And then moreover, this always works in the sense that a non-zero qx, y satisfying all the conditions and constraints will always exist. In fact, we already know that because this is where the idea came from. So the existence is clear since we already know that if we multiply the error locator with y minus f, then everything is as it should be. So let us see. So what does it take to understand this, to prove this? Well, actually not that much. So what does it mean that f of x is minus q0 over q1? Well, it just means that if I replace the variable y by the polynomial f of x, I should get the zero polynomial. So what I really have to prove is that q of x comma f of x is equal to 0. That's what it takes. So let us then try to get as much information as we can about this polynomial qx comma f of x. So first of all, what can we say about the degree of it? Well, we have now assumed these two degree constraints. So if we insert f of x instead of y, what happens here is that this first term, q1 of x times f of x, well, we know an upper bound on the degree of that because q1 has degree at most tau, f has degree at most k minus 1. So this first term, q1 times f, will have degree at most tau plus k minus 1. And Q0, the second part of the polynomial, has also by constraints here at most degree tau plus k minus 1. So the sum will have that degree as an upper bound as well. So whatever this polynomial is, the degree is at most tau plus k minus 1. But that's not all we can say. We can actually also say something about the number of roots this polynomial has. And the reason is that if I am not in an error position, so if I is not in script E, then what happens if I insert xi in place of x in this polynomial? Well, I get q of xi comma f of xi. But if there's no error, then this is the same as q of xi comma ri, simply because f of xi is equal to ri. But that's equal to 0 by the interpolation conditions that were posed on this q polynomial. So, indeed, this is equal to 0, and it means that q of x comma f of x, a polynomial in the variable x only, will have, well, it will have many roots in the sense that we know that the number of errors we assumed was at most tau, so it will have at least n minus tau roots. So n is the total number of evaluation points, so I had n interpolation conditions there, and for tau of them, they may not give rise to a root, but the others will. So I have a polynomial of degree at most tau plus k minus 1 with at least n minus tau roots. And then a simple calculation shows that this n minus tau is strictly larger than tau plus k minus 1, simply using that tau is n minus k over 2 rounded down. But that's great, because that, of course, we know that cannot happen unless we had the 0 polynomial. So, indeed, qx comma f of x is the 0 polynomial, which is the same as saying that f of x is minus q0 divided by q1. So this optimism is justified, and this is the main mathematical idea behind this very nice and simple decoder. But this formulation took a while to arrive, so this is not how it went historically. So I think this point of view can be attributed to Sudan, who actually let me say a little bit about that now. So what Sudan's idea was, he first of all thought of decoder in this way, but what he did, he looked at this expression q0 plus q1 times y, and started to wonder what happens if you also allow higher powers of y. So you could say, why would you want to do that? Well, maybe if you allow higher powers of y, you can still look at interpolation conditions and degree constraints in a suitable way and be able to show that your polynomial f of x is going to be a root of that polynomial. And maybe in that case, you can correct more than half the minimum distance error. And this is indeed the case. So if you allow higher powers of y and more coefficients, you can modify the degree constraints you would like to have. And if you do this, you can actually go beyond correction of half the minimum distance, but the price you will pay is that it might happen that the number of roots you have is more than one. So this f of x, the message polynomial, can then be a root of it, but it could have more roots. So this is why this gives rise to something called a list decoder. So your output will be a small list of possible code words, all close to the received words. So that is a list decoder, and then you can correct more than tau errors in some settings. So this Sudan list decoder, it worked really well for Reed-Solomon codes that have very low rates. So if the ratio k over n is less than, I believe, 1/3, you can go beyond half the minimum distance. Then just to complete this story, you can actually push this a little bit further. And this was an idea by Guruswamy. So Guruswamy, Sudan together came up with a modification of this, where you still allow higher powers of y, but now these interpolation conditions, you pose a multiplicity on them. So then you want that this q of xr ri is 0 with a certain multiplicity. And this gives rise to a decoder that in principle works for any rate Reed-Solomon codes. And for high rate, the improvement is small or very small. But for low rate, you get a nice improvement there. But since we also know that maximum likelihood decoding is NP hard, there is again some error radius popping up. So you cannot always decode with this. So these list decoders are just a variation of this idea. They are actually nice for another reason, but the reason is that originally Sudhir asked me to talk about decoding of Reed-Muller codes. But, unfortunately, I couldn't make new material in time. But in fact, there was an idea by Pelikan and Wu to think of a Reed-Muller code as a subcode of a Reed-Solomon code. And they used this to then decode the overlying Reed-Solomon codes. So we can actually use this idea also to decode Reed-Muller codes. But that's just an aside. So back to the situation we are in. So we have polynomials of y degree just 1. And we have just seen that this gives you an idea to how to decode Reed-Solomon codes. Because all we need to do is find this Q polynomial of the right form that satisfies interpolation conditions and degree constraints. And the first possible decoder would then be to say, well, let us look at these degree constraints. What that really means is that these two polynomials, Q0 and Q1, they are a linear combination of powers of x up to a certain degree, and then these coefficients of them that we don't know yet, so these indeterminates. So we introduce some indeterminate values Q0j and Q1j as the coefficients of Q0 and Q1. We know how many we allow at most. So, and then what are the interpolation conditions? Well, if we simply insert xr and xi and ri in it, we get a linear combination of these variables Q1j and Q0j that we want to be 0. So in other words, we get a linear algebra problem. We get, for each I, we get a linear condition on the unknown coefficients of the polynomials Q0 and Q1. And then we can use linear algebra to solve this. So this is a first possible decoder of a Reed-Solomon code. And not quite this, but one of the historically first decoders really goes along these lines. But again, the point of view is a bit different. But you see, this already tells you can, in polynomial time, decode Reed-Solomon codes up to half the minimum distance. So just to mention this one remark there was an old algorithm by Peterson that also solves a linear system of equations. And what basically happens, if you want to see the relation with this system, is that, well, the received word R only occurs here. So it only influences the coefficients of Q1. So this linear system, if we look at the coefficients of Q0, then only powers of the evaluation points are important. So xi to the j. So it means that if you would write down the matrix of this linear system, there's a whole part of it that doesn't depend on the received word at all. So you can actually already perform some Gaussian elimination and bring that part into echelon form. And if you do the bookkeeping, then this leads to a bunch of equations that only involve the Q1 of j. And these equations turn out to be the ones that Peterson also looked at. But anyway, that's again just a historical remark to see that all these decoding algorithms that exist, they are actually related with each other. But anyway, so we have a linear system in n equations in also roughly n variables, but we know that some non-zero solution will exist if the number of errors is less than half the minimum distance. So we can find that using linear algebra. So the running time of this would be, if you use naive algorithm, roughly cubic in the length of the Reed-Solomon code. Okay, so how to be faster than that? So what we need is a different point of view. So the point of view previously was to say, okay, I have these polynomials qx, y. I have degree constraints and I have interpolation conditions. So what I just did was say, okay, so let's first worry about the degree constraints, then about the interpolation conditions. And worrying about the degree constraints just means that I know how many variables I'm looking. I allow these, I know how many coefficients I allow my polynomials q0 and q1 to have. And then solve a linear system to deal with the interpolation conditions. But I'm going to do the opposite. I'm first going to worry about the interpolation conditions and then afterwards about the degree constraints. So what the idea is, one can actually write down all possible polynomials that satisfy the interpolation conditions. And so what does it look like? So we will need two help functions. So what we need is a polynomial that vanishes in all the evaluation points. We call this capital G. And we need a polynomial, capital R, that interpolates the received word. So that satisfies that R of xi is equal to Ri, the ith coordinate of the received word. So since we have n coordinates, we know that the polynomial of degree strictly less than n will exist that satisfies this. And from last time, we can also use this Lagrange basis to just write down a formal expression of it. So we have these two polynomials, and now the lemma is that any polynomial of the right form, so q1 times y plus q0 of x, there's a small typo there I can see. So this will satisfy the interpolation condition even only if it is of the following form. So some polynomial times this polynomial g plus another polynomial in x only times y minus r, where r was this Lagrange interpolation polynomial. So in other words, if we think of this as a module over the polynomial ring, it is a rank 2, free rank 2 module, and the generators are g of x and y minus r of x. Now, first of all, why do these two separately satisfy all the interpolation conditions? Well, so g of x itself, if we replace x by any of the evaluation points, we get 0. That's how it was constructed. So the variable y doesn't occur at all here, so that has no influence on the outcome. So g of x will definitely satisfy all the interpolation conditions, but so will y minus r. Simply because if I replace y by ri, and I replace capital X by x of I, by the property of this Lagrange interpolation polynomial, the difference is going to be 0. So also y minus r of x is indeed a polynomial satisfying the interpolation conditions. So definitely any combination like this, any linear combination, linear meaning now over fq of x, will satisfy everything, all the interpolation conditions. So conversely, if we have a polynomial that does satisfy this, well, what we simply can do is, first of all, we can subtract a suitable multiple of y minus r of x from it, and the resulting difference will still satisfy all the interpolation conditions, but now it's a polynomial in x only, so it's a univariate polynomial. And then satisfying all interpolation conditions means that all the evaluation points xi are roots of this. But then, of course, if we work with univariate polynomial, having xi as a root means x minus xi is a factor. So that means that in the end of the day, this difference will be some multiple of g of x. So indeed, we can write down rather succinctly all possible polynomials satisfying the interpolation conditions. Okay, but now we have to worry about the degree constraints. So this is the price we now pay. We now solve the other half first, but now what about the degree constraints? Okay, well, so let's take a step back. I mean, what we really showed is that if we are looking for this pair Q0, Q1, what it is going to be, it is going to be in an element of the row space of this matrix, Gx0 minus R of x1, and the row space over Fq of x. So again, we have a rank 2 module now over the polynomial ring. And what we want is an element that satisfies the degree constraints, but these can be, so to say, abbreviated in one way. So we can define the k minus 1 degree of a pair of polynomials a of x comma b of x by saying that it should be equal to the maximum of the degree of a and then the degree of b plus k minus 1. And we call that the k minus 1 degree of this pair of polynomials. And then what the degree constraints mean is that we are looking for an element in the row space of that matrix that has k minus 1 degree, at most tau plus k minus 1. So this is just a reformulation of the degree constraints. Okay, so this is what we need to do. So somehow we need a way to find elements of low k minus 1 degree in the row space of this matrix over the polynomial ring. All right. So this is what we need to do. So in general, this looks a little bit just as a reformulation, not something that makes life easier, but in fact it does. So let us take a look at what we can say about this. So yeah, the idea is to study these type of matrices, row space of these type of matrices first. And there's one particular case where it is very easy to find an element of low k minus 1 degree. And this case is the following. So we call a matrix K reduced if two conditions are satisfied. So it's a condition on the degrees. So we could say that this K minus 1 degree, it is basically taking the maximum of the degree of the first elements in the first column and of the second column plus this K minus 1 to make it fit with the decoding description. But then we can think of this as a kind of a Gröbner basis property or something like that. And we can say that it's K reduced if the dominating term in the first row is the first polynomial and the dominating term in the second row is the second polynomial. So what it really means, we have these two inequalities. And if there is a tie, then we choose the first one. So we have these degree of the first and the second coordinates, and we just want a matrix where the diagonal elements are, to say, the dominating ones. And why are these K-reduced matrices interesting? It's simply because one can prove that if you have a K-reduced matrix, and we are looking for an element in the FQ row space, not just of low degree, but of minimal possible degree, then it's either the first or the second row. So to put it in a different way, any elements from this row space of the matrix will satisfy that its K minus 1 degree is either larger than or equal the K minus 1 degree of the first row or of the second row. And the proof is a bit technical, but not hard. And as you can see, it's not very long. So I don't know if I really should go through all the gritty details here, but the main observation is that let us suppose that we pick an element from this row space. So that just means that we can find two polynomials b0 and b1 such that b0 times p00 plus b1 times p10 is a, and similarly for b. So that is just what it means to be in this row space. So if somehow this b would have strictly smaller k minus 1 degree than let's say the first or the second row, this gives us some information. So let us, for example, assume that the k minus 1 degree of a comma b is strictly less than the degree of p00. So what does that mean? well, if the degree of A is really smaller than the degree of P00, then we can see that some cancellation will have to occur. So the idea is to use these K-reduced conditions to say, well, if that would happen, for example, for the first row, then we can conclude something. We can say then that the x degree of A would have to be strictly smaller than the x degree of P00. And that means that on the left-hand side, some cancellation must occur. Yeah, so if the degree is bigger for this one, for P00, and we're multiplying something with it, then the only way the degree can drop to that of A is if cancellation occurs in the first product and the second product. So we can conclude, in particular, that these two have exactly the same degree. And that is enough. So these kind of observations will lead you to and similarly for B, will lead you to have cancellation in both equations, star and double star, and then we can just use the inequalities we have from the assumption that it was K-reduced and find a contradiction. So these K-reduced matrices, they are nice. We can actually find an element of very low, actually of minimal K-1 degree immediately. So K-reduced matrices are nice, and what we need to do somehow is, if I just go back again, so what we had was this matrix, G0 minus R1. Well, that is in general not going to be K-1, it's not going to be K-reduced because, well, the first row is actually fine. This degree of this dominates that of 0. But the second row, that is in general the problem. So the degree of this Lagrange interpolation polynomial is typically just going to be n-1, but it could be lower, of course. But let's say it is n-1. So then the degree of this will exceed the degree of this constant 1 by so much that it is actually not K-reduced. So we do not have a K-reduced matrix. So we somehow have to try to find a way to transform this matrix that we start with into a K-reduced matrix. Now, if we can somehow do that, then that would be fine, because then not only can we find an element of low enough degree in the row space, we find actually one of minimal possible degree. So if we can do that, we can do more than what is needed. So, okay, so again, what did we have for the decoding? I just repeated the basic assumption here. So we have a G, we have a Lagrange interpolynomial, and our assumption on the number of errors that have occurred. So if we can somehow transform the matrix we have into a K-reduced one, without changing the row space of the matrix on the way. So in other words, the only thing we can do are elementary row operations over the polynomial ring FQX. So if we can do this, then we can immediately, from the matrix P we have obtained, select which row has the smaller K-1 degree, and that is going to be a valid pair Q0, Q1 that we were looking for. Okay, so if we don't have too many errors, so at most n-k/2, we know that the pair Q0, Q1 we would find in this way would be the right one. And that is simply because we know already of a pair that existed. Again, if we use the cheat code for this game, so to say, we know there's the pair for Q0 minus f times lambda, where lambda was this error locator, and for Q1 lambda itself. So we know a non-zero solution exists in this row space that is valid, and we would actually find that one. So if more errors occur, then things can go wrong. Then the output could be either nothing exists of that K-1 degree, or you find something, but the polynomial doesn't have roots or those kind of things. So it will go wrong if there are more errors, but otherwise everything should be fine. But the big question is now, is there an efficient way to go from our input matrix to a K-reduced one? That is now what we need to think about. Okay. So let us see if we can do that. And the algorithm is rather simple, if you have seen it. So what do? We simply have an algorithm that takes our input matrix, and then if the matrix is not K-reduced, you replace it by another one. And what do you do? So what we do is we move the second row up to the first one, and the other row will be determined by using an elementary row operation. And what you need is to divide P00 and P10 and use division with remainder. So in our case, this polynomial G has degree n. The degree of R is strictly less than n. So it means we can perform some division, and we have a quotient S and a remainder T. And what we basically do is that this other row is obtained by taking the difference. So we take this, we take the first row and we subtract S times the second from it. So in the first coordinate, we get P00 minus S times P10, so that's the T. And for the other, we do the same thing. We take this one minus S times that one. So we end up with P01 minus S times P10. So this is indeed something that did not change the row space, because we essentially multiply the original matrix with a unimodular one, with something that has a determinant, an element from the finite field, actually determinant minus 1. So that did not change the row space, but the idea is now that we somehow got closer to being K-reduced. So the intuition is that the problem was this second row. So this R simply has too high an X degree in general. So if we do this just in one iteration, what happens is that this row is moved up. So if it is in the first row, this would be fine, because we want the first element to have high X degree compared to the next one. So at least K minus 1 higher. And what happened in the second one? Well, we have replaced this G of X by something of lower degree. So at the very least, and we have replaced the second coordinate potentially with something of higher degree. So the degree of T is going to be lower than what G was before, and also the degree here is going to be higher of the degree what it was before. So somehow the second row, it may still fail. It may not be K reduced after one iteration, but it is more balanced. So what is going on is that in every iteration, you get a division with remainder, the remainder having a small degree as possible. So if we iterate this, every iteration, this quotient is going to be some polynomial of positive degree. And what that really means, if you work out the gritty details, is that the degree of every iteration of this coordinate 1, 0, the element there, is going to increase. The degree of this 1, 0 is going to decrease. The degree of the element in position 1, 1 is going to become larger and larger. So this new row is every time it's more and more balanced in this K minus 1 degree sense. So there must be some iteration at some point where it was not okay previously. So it was not K minus 1 reduced in iteration T minus 1, but it is in the next iteration. So remember that the second row is K reduced if in strict inequality like this here is satisfied. So the degree of the first coordinate is strictly less than the degree of the second plus K minus 1. So since the degree of this one is decreasing, of P11 is decreasing, there must be a case where it wasn't satisfied in one iteration, but it is in the next. But then what do we have? Well, if we then just simply look at what the matrix looks like, so remember that in one iteration, the first row is the second one of the previous one. So it means that if we pick this T iteration, what happens is that we find a K-reduced equation, K-reduced matrix, I should say. So indeed, this is going to work, and we don't need that many iterations for this. So what we need to do, since the degree will drop at least by 1 in every iteration, we need something like the order of magnitude, well, maybe the worst case would be something like 2n. So big O of n iterations of this. And then we need to do this division with remainder. But everything is going to have a complexity that is quadratic in the length of the Reed-Solomon code if we do it like this. So this is faster than the cubic complexity from the linear algebra approach. So basically, we described all the polynomials q, x, y that we would like to have that satisfy the interpolation condition, modify the matrix we have to a k-reduced one using this simple algorithm, and then one of the rows is going to give us the pair q0, q1 that we are looking for. So this is a very nice way of looking at things. So this division with remainder is, of course, also used in the Euclidean algorithm. So if you have a Euclidean algorithm, if it's for number or for polynomials, you do something like this. And in fact, if you look at the extended Euclidean algorithm, then you can also find polynomials such that the linear combination, so to say, of the two input values on the first column give you something that's equal to the GCD of the two. And what is the extended Euclidean algorithm? If you run it on the pair G, minus R, well, you basically do exactly this, but maybe you continue for a while. You continue till you get the 0 element in the first column. But in principle, you would do the same, except that you would run it on the matrix G10 minus R01. So this is why very often this way of decoding is also called the decoding using the Euclidean algorithm. And in that fashion, this is the way Gao looked at it and published this. So the Gao decoder is essentially this. There are other ways to decode Reed-Solomon code, so maybe I can use the last minutes I have to just say a little bit about this. So historically, the first decoder that uses the Euclidean algorithm is not this one. It is an algorithm by Sugiyama. Again, everything is connected. So what we have here is this polynomial G and this polynomial minus R. So those that know what happens in this Sugiyama algorithm, so what happens is that instead of G, you have a power of x to the n minus k, and instead of minus R, you have a polynomial that involves so-called syndromes of the received word. But the only way, the trick you need to go from this to that decoder are two things. So if you have a Euclidean algorithm and you want to figure out what is the GCD, well, I suppose you need everything. You need G and R as complete polynomials. But that's not what we want. What we really want is to lower the degree for a bit till it's low enough so that you get a K-reduced matrix. And if that's your only goal, to find a linear combination of G and R over the polynomial ring that has low enough degree, you don't need the small order terms of these two polynomials. So what you can do is you can get rid of the degree k minus 1 and smaller coefficients of both of these and run the Euclidean algorithm on that. Then you would stop at exactly the same time and you would get the same output. So somehow that is the trick to do that instead. And that would lead you to this Sugiyama decoder. So also that is closely related to this. So maybe those of you that have heard about decoding Reed-Solomon codes before have worked with the Berlekamp-Messi algorithm. That has quite a different flavor. It has been shown to be completely equivalent to the Euclidean algorithm decoder. But there that's a different game. So there again, you would need the so-called syndromes and then try to produce a linear feedback shift register, an LFSR, that produces those syndromes. So you want an LFSR of smallest possible length that produces those syndromes. And that is what the Berlekamp-Messi algorithm does. And then the characteristic polynomial of the resulting LFSR will actually be the error locator, but that would require more. So that is how this comes in. Okay, so I think that is more or less what I wanted to tell you. If there are any questions, please go ahead.
Thank you, Peter, for this beautiful exposition. I guess it's open for questions.
Yeah, if not, I can maybe just say that all these ideas, especially for the Sudan and Goswami Sudan, they also work for more general classes of code, including algebraic geometry code, which is really my main area of interest. I just want to point that out, that this is still ongoing research in that end. It's still open how fast you really can decode algebraic geometry codes. So for Reed-Solomon codes, there are ways of implementing these decoders that run extremely fast, at least in theory. So I talked about complexity quadratic in the length, but you can actually do better than that by using tricks that implement the Euclidean algorithm in a much faster way. So then you get close to linear time in the code, so big O of n. But that's not quite true. You get big O of n times logarithmic factors in n. So that is the state of the art.
And you can do it for any algebraic curve.
Well, yes, in principle, yes, but not with that speed. So that is still a problem. So you can do also these kind of tricks with using row spaces of matrices. So that is possible, but it is not. It is not known if you can actually get close to linear time for decoder, for AG codes. That is, nobody knows that.
Mm-hmm. And where can one find a good exposition of the Berlekamp-Messi approach? Well, you have anything on that?
I really prefer thinking in terms of modules. But there must be many, actually. I think Messi himself has written expositions about that. But I can send you, I can find you a precise thing if you're interested.
Any other questions or comments? Let's see. I guess not. Well, I guess you left speechless. But, so thank you really for this wonderful talk. And I know how busy you are and finding time and doing these two lectures on suggested dates. We really appreciate that.
That's my pleasure.
Those images, maybe PDF or something, we'll be happy to upload them on the web page of your whiteboards.
Okay, I'll send you what I have. Yes.
Okay. I guess we have a good half an hour break now before the last talk, and that will be by Sartaj, right? It's okay. You're muted, no?
Oh, yes, I'm muted actually. Yeah.
So you would give the last talk, I believe. Right?
Yeah, yeah. As per schedule, yeah, I'm the one.
Yeah. Okay. Thank you so much. And you're around virtually, physically, etc.
Yes, absolutely.
Okay, bye for now. And okay, I'll come back, of course, for Satyaj's talk. correct. Hi, Satyaj. You ready, huh?
Yeah, can you hear me?
Yes.
Okay, okay. So let me share my slides. So I guess it's time. Hello.
Yeah.
Can you see the slides?
We could see them a minute ago. Now we are back to the...
Now? Yeah, is it the slides are visible now?
But you open them in a browser. I don't know if you can do a full screen there.
No, full screen. Okay now?
Yeah, it's okay.
Okay.
Yeah, like this. But maybe, you can...
Just a minute. I'll just adjust it. Give me a minute.
You can open the...
Can you see the slides now?
Yes.
Okay. I've just tried to write. Please let me know if it is okay. Can you see the?
Yeah.
Okay, great. Okay, thank you. So, thank you. So I'll just. Okay. Okay, I'm sorry, I'm a little bit late. So anyway, so I'll just, I mean, I have already discussed why are we studying stream ciphers, because they are easy to implement in many hardware implementations. When it comes to hardware implementations, I think LFSRs, they suit well because they require very less memory. So whenever there is some encryption scheme is to be handled over a tiny device, then stream ciphers are quite useful. And we have seen that GSM is something where this stream ciphers are being used. And stream ciphers are basically we have key stream, and then key stream has to be pseudo random sequence in order to have security. If it is not pseudo random sequence, if it has pattern, then it is easy to break. And this is the model of typical stream cipher that we have actually. So from short key, we will generate a key stream. So designing a stream cipher means effectively we have to design a strong key stream generator. So short key will give you a longer key, and then encryption and decryption function are quite easy to, they're just XOR operations. So that is what we have discussed, and this was A51 GSM. And then we also discussed what is called LFSR. So I gave few examples of LFSRs. So today I'll try to discuss some more things about LFSR, because they are the object that will be useful to us when Samrit would be discussing some advanced things concerning LFSRs, some generalization of LFSRs. So let me quickly recall the example, and then we define what is an LFSR. So if you remember last time, so we begin with three registers, and these are three registers, and we are taking output from here. And my function is basically I'm just adding these 2 bits. And this bit I am not adding, but I'm just writing it out, and then we are zarring it out, and then we are giving feedback to this. And this is my initial state, S0, S1, and S2. So usually initial state we will denote by capital S, which is this vector, S0, S1, and S2. And these are the multiplies. C0 is 1, C1 is 1, and I'm putting C2 equal to 0 because I'm not including this register while I'm computing the linear feedback. So then the recurrence relation that we have is this, Si plus 3 equal to C2 Si plus 2. I'm sorry, Si plus 2 plus C1 Si plus 1 plus C0 Si, and I equal to 0, 1, and 2, so on. So we can generate an infinite sequence. So now, corresponding to this linear recurrence sequence, this is a homogeneous linear recurrence sequence, recurrence relation, homogeneous linear recurrence relation. So this is an example of an LFSR of length 3 over the binary field, over F2. And this length 3 is also sometimes in literature, for example, Solomon Golomb calls it 3-stage LFSR. In his book, he calls 3-stage LFSR, the 3 registers. Some people also call it that it is LFSR of degree 3. So there are various nomenclatures of degree 3. So this is what the LFSR is. Now, corresponding to this linear recurrence relation, we can associate a polynomial. And this polynomial I can associate like this, fx equal to, this is a 3-stage LFSR. So x cube plus c2 x square plus c1 x plus c0. So this is the polynomial. So effectively this is x cube, c2 is 0 in our case, and 1. So this is the polynomial. And then I left one exercise, that what is the order of this polynomial. So if someone has computed it, please let me know. Otherwise, I will just write it. So the order of this polynomial would be 2 to the power 3 minus 1, which is the maximum possible, which is 7. So corresponding to any LFSR, so LFSR can be, this is the pictorial view of LFSR, but we have a very nice homogeneous recurrence relation to define an LFSR, and we also associate a polynomial, and this polynomial has the order 2 to the power 3 minus 1. So it is a maximum possible order. This is a polynomial in F2x. So its order cannot go beyond 2 to the power 3 minus 1. The order was defined by Professor Samrit Ram in his first lecture. And also we can associate a matrix corresponding to this. So the matrix, so therefore, since the order is maximum, so this polynomial is basically primitive polynomial. Primitive polynomial of degree 3. And it turns out, I also explained to you, so if you take any non-zero initial state, if you take everybody 0, then you get a 0 sequence. And 0 sequence is not useful to us, because if we use 0 sequence, then masses goes in plane. And so is the case with if all 1-1 sequence is also not useful, because all the bits will be flipped. So that is what we are going to get. So we have to get something which looks like random. So it turns out that if you take LFSR of maximum period, they do satisfy statistical properties that are required for a pseudo-random sequence. And also they give a very large period. So here we have taken last time, one state, initial state, and it turns out that the period of that sequence was 7. Now corresponding to this matrix, I can also associate a matrix corresponding to this polynomial. So that matrix is nothing but its companion matrix. So it's going to be 0, 0, 0. It's a C0, 3 cross 3 matrix it is going to be. And 1, 0, C1, 0, 1, C2. So which is effectively this matrix, 0, 0, 1, and 1, 0, C1 is also 1, and C2 is 0, 0, 1, 0. So this is the matrix. Now the the property of this matrix is, so you have this initial state, for example. Initial state is my S0, S1, and S2. What is going to be my next state? Next state is going to be, because we are taking S0 to be the output, so next state is going to be S1, S2, and S3. So what is S3? S3 would be determined by the recurrence relation, which is nothing but S2 plus S1. When I say here plus, actually it means XOR, because we are over the binary field F2. So now the matrix is interesting in the sense that, so instead of using this notation, maybe I will use another notation. Let's say call it T. This is nothing but the companion matrix of the polynomial. So if you multiply this S0 with this matrix T, you can see that immediately you are going to get, the next state, that is capital S1. So next state means, whatever the entries are here, that I call state. So, okay. So this is the initial state. We begin with S0, S1, and S2. When S0 shifts here we will get S1, S2, and S3. So that is the next state. So total possible non-zero states are 2 to the power 7 minus 1. These are the only possible non-zero state. So in general, we can say that if I have to compute the kth state of this linear feedback shift register, so that is as good as multiplying this initial state by the kth power of this matrix, because my S2 is going to be S1 times T, and this is S1 is nothing but your S0T multiplied by T, which is going to give me S0 T squared, and this can be generalized. So this is what I'm going to get. So this is what so an LFSR can actually, it is being described only by these the multipliers C0, C1, etc. C0, C1, and C2. So they determine this complete LFSR. So even if you don't understand, yes, is there any question?
Yes, Satraj, did you say 2 to the power 7 minus 1?
Oh, did I wrote that? Oh, no, it should be 2 to the power 3 minus 1.
But no, because you said total number of non-zero states is 2 to the 7 minus 1, that might cause.
Oh, I wanted to say total number of states are actually 7.
Yeah, that's, I'm sure.
I'm sorry about it.
No problem.
Yeah. So this is how, so this matrix is usually known as state transition matrix, because this helps you to get another state. So this in the literature is known as state transition matrix. And this polynomial that we have associated with respect to LFSR, this is known as characteristic polynomial. Polynomial of LFSR. And these LFSR is also useful, like in Professor Peter Bellin's lecture, he was saying that in decoding of BCH codes, or maybe, so you need actually LFSR. So there is something called Berlik and Massey algorithm. So that determines actually the minimal polynomial. If you are given any arbitrary sequence over a finite field, then what is going to be the degree of the least LFSR that generates that sequence? So that is known as linear complexity. So basically, that also gives the polynomial corresponding to that LFSR. So that Berlik and Massey algorithm that helps us to determine the polynomial of an LFSR, a polynomial of least degree that will generate that particular sequence. Anyway, so now this is the example that we have done. Now we are going to define them more formally actually. So I'm coming to that definition. So, okay. Yeah. So just a quick recap. This is something done by Samrit Ram, that if you are in the polynomial ring, then there is a least positive integer e such that fx divides x to the power e minus 1, where fx is polynomial of degree n and f0 is non-zero. And we define order, and the polynomials are maximum possible order. They are known as primitive polynomials. And he has also proved what is the number of primitive polynomials. So that is something has already been completed by him. So I don't have to spend time on it. Now coming to some more definitions. So here are some definitions. So suppose you have an arbitrary non-empty set S, and suppose S0, S1, etc. This is a sequence of elements of S, and if there exist integers r bigger than or equal to 1 and n0 bigger than or equal to 0, such that Si plus r equal to Si for all I greater than or equal to n0, then the sequence is called ultimately periodic sequence. So that means you have to ignore first n0 minus 1 elements of the sequence, and after that it actually starts repeating. So Si plus r equal to Si for all I bigger than or equal to n0. So that means that you ignore first n0 minus 1 elements of the sequence, and then it starts. So that is why it is called ultimately periodic. So it is not periodic right from the beginning, but if you ignore few elements of the sequence, then it becomes periodic. So it is called ultimately periodic, and R is known as the period of the sequence. And the smallest among all the periods, possible periods of an ultimately periodic sequence is known as least period of the sequence. And here is an easy exercise that least period always divides every other period of the ultimately periodic sequence. So this you can try by yourself, maybe by using somehow you may have to use division algorithm here. An ultimately periodic sequence S0, S1, etc. and so on with least period R is called periodic if Si plus R equal to Si holds for all I equal to 0, 1, etc. So that means the sequence starts repeating right from the first element. So we have the sequence S0, S1, etc. And then when we get SR is going to be equal to S0. SR plus 1 is going to be equal to S1. So right from the first elements itself, it starts repeating. So then the sequence is called periodic. Okay. So if you have an ultimately periodic sequence with least period R, then the least non-negative integer n0. So among all n0s, you choose the least one. That is called the pre-period. And sequence is precisely periodic if the pre-period is 0. That means it starts repeating right from the beginning. So if n0 becomes 0, that means your sequence starts repeating I will be greater than or equal to 0 in that event. So if the pre-period is 0, then your sequence is periodic. So these are the definitions of ultimately periodic sequence and periodic sequence. Okay. Now I'm coming to a definition of linear feedback shift register. So this is the definition of linear feedback shift register. So linear feedback shift register of order n over a finite field FQ is nothing but it is defined by a homogeneous linear recurrence relation, which is given by this. So the pictorial view, if you want to draw a picture of this, then it will look like something like this. So we have here a 0, and maybe we have here S1 and Sn minus 2. Maybe I can erase this. And Sn minus 1. So these are the initial, this is the initial state. And we just have multipliers. So here we have C0, C1, and Cn minus 1, and then we add them. So here this need not be zar. So now this addition is happening in the field, and then you take this feedback. So this is the general view. So here if you look at my elements, this C0, C1, etc., Cn minus 1, I am now taking from the field FQ. They are not from F2 now. And this addition here is addition happening in the field FQ. So it's not XOR operation anymore. But of course, if you take Q equal to 2, then it is an XOR operation. And this multiplication is also happening in the field. So these Ci's are elements of field. S0, S1, Sn minus 1, they are also elements of finite field FQ. And therefore, this multiplication is happening in the field. This multiplication is happening in the field. And then addition is also happening in the field. So we are defining now linear feedback shift register of order n over an arbitrary field FQ. And if you don't know what FQ is, then you can think of FQ is nothing but just your binary field F2. And then you think of these additions and XOR operation. And this is called the initial state. So the definition is same as what we have in the example. Okay. Now, if you have this LFSR, then it turns out that the sequence generated by this LFSR1, that is actually ultimately periodic. And such that its least period is bounded by q to the power n minus 1. So its least period is less than or equal to q to the power n minus 1. So I will just sketch the proof of this theorem. And the next theorem says that if C0 is non-zero, then it turns out that the sequence is actually periodic sequence. And of course, period is less than or equal to q to the power n minus 1. So I'll just sketch the proof of these two results. And then we'll do some more things. Okay, so the theorem 1, the sequence generated by LFSR that we have defined is ultimately periodic, and the least period is less than or equal to q to the power n minus 1. This is what we have to prove. So this is the least period times. Okay, so the proof of the first theorem. So we consider here two cases. So case 1, so if my initial state is 0, let's say, all 0 elements. So is 0, 0, 0, 0, 0, this n tuple. So if this is the initial state, then the period, the least period of the sequence, okay, so maybe I have not told you. So the sequence, the infinite sequence generated by this homogeneous linear recurrence relation, I denote it by S infinity. So S infinity denotes the sequence elements, all this infinite sequence. So the least period of S infinity is actually 1, which is of course less than or equal to q to the power n minus 1. So there is nothing to prove. Now case 2, if this initial state is not 0, then we consider the following states. So I consider S0 and then next state S1 up to S q to the power n minus 1. So these are total q to the power n states. So total q to the power n non-zero states. But we know that total non-zero states are going to be only q to the power n minus 1, because this S0, these S0, S1, they are basically all elements in f q to the power n in this vector space. And so total non-zero elements in this vector space are going to be only q to the power n. So we are going to get only q to the power n non-zero states. So therefore, at least 2 of them have to be the same. So therefore, there exist integers, let's say I have already used somewhere. So maybe j and k, maybe I will put here, less than k, greater than or equal to 0, less than or equal to q to the power n minus 1, such that the jth state is same as the kth state. Now using this actually, and using the recurrence relation that we have defined, the LFSR things here, this recurrence relation, using this relation, we can actually, and by induction, we can actually prove that. So this, so using recurrence relation, one, and by induction, one can see that this Si plus, so K is bigger, K minus J is same as okay, J plus 1.
Excuse me, sir, we apply induction on N.
Sorry?
We apply the induction on states N, Q raised to power N. We apply induction on N. Is it?
No, here, induction on N, you are saying? No, no, I'm not applying induction on N. Just a minute, just give me a second. I'll let you,
okay, sir.
Just a minute, I have written down somewhere in my notes. Okay, so, yeah. So I plus K minus J is same as Si for all I bigger than or equal to, oh, I'm using different symbols in my notes. Anyway, equal to J. So let me see, if I equal to J, then what happens? I equal to J, then in that case, okay, sorry, this is I.
You want
so sorry?
Yeah, that's correct. What you have.
Yeah, this is correct actually. I equal to J, then if I take I equal to J plus 1, then I would effectively get K plus 1 equal to S I plus 1 and so on. Yeah, so this works actually. Yeah. So you can apply induction on I actually. You can apply induction on I as well as maybe on, so we can also say that I minus J is bigger than or equal to 0. So we can also apply induction on I minus J actually. So it will work actually. So is that clear or not? Somebody had asked.
Yes, sir.
Okay.
Can you show just one step for induction? Little bit doubt still.
Sorry?
Please, if possible, please show one step of induction.
Okay. So if you take I minus J bigger than or equal to 0, so I am taking I minus J equal to 0. That effective means I am taking this case. So this case, it is already true, right? If I take I minus J equal to the next step, for example, then that is also true actually, right? This is this system. And then we assume that it is true for, okay, just a minute. Am I?
It's okay, I think best is from induction. Just Sk is equal to S, Sk plus 1 equal to Si plus 1.
Yeah. Okay.
And so on.
Yeah.
Okay, sir. Okay, thank you, sir.
Okay. Yeah.
Just notationally confusing, perhaps on the spot.
Okay. So. Okay. So therefore, we have this actually. So this means that this states, states itself are getting repeated. The period of these states is basically K minus J. If you take the sequence of states, so that period is, we get one period K minus J, which is less than or equal to Q to the power N minus 1. And if the states themselves are repeating, that means the sequence is also repeating. And this sequence is basically ultimately periodic sequence. Right? So this shows that the sequence is ultimately periodic with least period less than or equal to q to the power. So with least period, in fact, r is less than or equal to, what is that, k minus j, and which is less than or equal to q to the power n minus 1, because the period has to be less than or equal to k minus j. So, and this is less than or equal to q minus 1. So this is done actually. Now the next theorem is that if C0 is non-zero, then S infinity is periodic. The sequence generated by LFSR. This is periodic. So this proof, again, let me write few steps. So anyway, this is S infinity. Anyway, we know that this is ultimately periodic. So suppose that least period is R, and pre-period is N0. So that means Si plus R equal to Si for all I greater than or equal to N0. So this is a number greater than or equal to 0, and this is a number bigger than or equal to 1. So we need to show that n equal to 0. In order to prove that it is periodic, so pre-period has to be 0. To show that N0 equal to 0. So we will assume on the contrary that N0 is not, N0 is strictly bigger than 1, let's say, bigger than or equal to 1. Then we must get some contradiction. So here I just put, I take I equal to N0 plus R minus 1. And I put this in our recurrence relation. So what was my recurrence relation, if I remember it correctly? Si plus n equal to Si C0 plus Si plus 1 C1 and so on. Si plus n minus 1 Cn minus 1. This was the recurrence relation. I is bigger than or equal to 0. So I just plug this value here, from here to here. Then what I get is, I am directly writing the step, or maybe I can write it, that N0 plus R minus 1 plus N equal to S N0 plus R minus 1 C0 plus S I plus 1. That means N0 plus R minus 1 plus 1 C1 and so on, N0 plus R minus 1 plus N minus 1 Cn minus. This is what I get. So from here, I can write this as N0 plus R minus 1 equal to C0 inverse and this term. Minus 1 plus n minus this term. So this is, anyway, 1 will get cancelled. This will get cancelled. So what I will get is just this C1 and minus 1 minus Sn0 plus R minus 1 plus n minus 1 Cn minus 1. So this is what I am going to get. Oh, I'm not. So maybe I will write and erase this step. I don't have enough extra slides. Actually, I was just thinking that I'll just give the sketch of the proof. But anyway, so it's more or less done. So if you look at this, so Sn0, yeah. So this I can write as Sn0 plus R is basically Sn0. So this I can write as, so this again I can write, so I can remove here R from here. And similarly, I can remove R from here. And I can also remove R from here because R is the period. So basically I will get this. And it turns out that again, this is nothing but your Sn0 minus 1. If you put I equal to, so this I will get. So if you take I equal to N0 minus 1 in the recurrence relation, this thing, then you will see that this quantity will come out to be Sn0 minus 1. So what we have is basically this thing, that Sn0 minus 1, this thing, plus R becomes Sn0 minus 1. So which is the contradiction to the definition of pre-period. Because pre-period is the least positive integer that satisfies this condition. So this contradicts actually. So this assumption was not correct actually, this assumption. So therefore the pre-period is 0. So now coming back to the next slide again. So what we have done so far is we have this linear feedback shift register of order n, and we have an initial state. Then it turns out this sequence is ultimately periodic and its period does not go beyond q to the power n minus 1. And it is precisely periodic if you take C0 to be non-zero. Then it turns out to be periodic. So now we make another definition. We say that this LFSR is primitive LFSR if it turns out that if it attains the maximum possible period irrespective of the choice of the non-zero initial state. So the example that we have done actually, so that is actually the primitive LFSR. Because if you take any non-zero initial state, then it turns out that you always get the period 7. So the example that we have earlier taken is actually the primitive LFSR. So primitive LFSR is an LFSR which has got the maximum period irrespective of the choice of the initial state. And they are of our interest because for designing stream ciphers, we want LFSRs that can give us, we want sequences of maximum possible period. So that is why these primitive LFSR are of our interest. Now, as you have seen that the polynomial that we have associated corresponding to that example, that polynomial was x to the power q plus x plus 1. That was primitive polynomial. So we have primitive LFSR which has got maximum possible period. We have got primitive polynomial which has got maximum possible order, that is q to the power n minus 1. So therefore there has to be some sort of relationship between them. So here is the relationship, and that will also give me the question answer to this question. What is the number of primitive LFSRs of order n over fq? What is this number actually? What is the number of primitive LFSR of order n over fq? So that number is basically given by Euler-Tauschent function q to the power n minus 1 divided by n. So this happens because this LFSR is primitive if and only if the characteristic polynomial. So here, this is the characteristic polynomial. X to the power n minus cn minus 1, x to the power n minus 1, and so on, minus c1x minus c0. So here, we did not take negative while we were discussing the example because we were over the finite field we were over binary finite field. So minus and plus are same. But here I have taken minus sign. So this is called the characteristic polynomial. So if this is the primitive polynomial, then your LFSR turns out to be a primitive LFSR with maximum possible period. So we will see some more things about this. But before that, let's look at what is called it's again characterization in terms of matrix actually. So corresponding to LFSR, we can associate this polynomial that we call characteristic polynomial, and we can also associate a companion matrix like this. And this companion matrix, the determinant of this companion matrix is minus 1 to the power n plus 1 C0. And if C0 is non-zero, so C0 is nothing but f of 0 basically. If you take f of 0, that will give you. So C0 is non-zero, that means f of 0 is non-zero, then this polynomial is basically invertible matrix. So it goes into the general linear group GLN FQ. So if C0 is non-zero, then this state transition matrix, that is actually a non-singular matrix and is the member of a general linear group of order n. And similar to the example, if you want to determine kth state of the LFSR, this is not 2 actually, this should be 1. Of LFSR 1, that is obtained with the help of initial state. So you just multiply the kth power of your transition matrix by the initial state, you can get the kth state for any k bigger than or equal to 0. So that is something we have already observed in the example. So I gave example first because I thought maybe it would be easier to understand the things better, in a better way. Now coming to matrix group over finite field. So we have this general linear group and we know that its cardinality is given by this. Then the question is, what is the maximum possible order of an element of GL and FQ? So the answer is given by this. So the maximum possible order of any element in the general linear group can be this. So if you take any element in the general linear group, which is a finite group, and we know, of course, the order of this, then the order of this element is always less than or equal to q minus 1. So, and one can prove that order of A is precisely q to the power n minus 1 if and only if the characteristic polynomial of A, just denote by chi of A, chi of x, is primitive of degree n. Of degree n. So the proof is not difficult. Maybe I'll just give a quick proof. So suppose this px is the minimal polynomial of A. And since this is invertible matrix, so 0 cannot be its eigenvalue. So therefore, this P 0 is, never a root of this polynomial, not 0. And for any positive integer E, it is easy to observe that A to the power E is the identity matrix, where I is n cross n identity matrix over the finite field FQ. If and only if this Px divides x to the power E minus 1. So from here, what is clear is that order of this matrix in the general linear group is same as order of the polynomial Px. So these two are same. Also, since this is the minimal polynomial, and therefore Px would divide the characteristic polynomial. So that means that this degree of Px is basically less than or equal to degree of the characteristic polynomial, which is actually n in this case, because A is matrix of order n. So we have this polynomial where P0 is not equal to 0 and degree of Px is less than or equal to n. So this implies that this order of Px is basically less than or equal to q to the power n minus 1. Of course, this Px is a polynomial in FQX. And so is the case with characteristic polynomial. So therefore, if you look at here, so therefore the order of A is less than or equal to q to the power n, always. So order of any element in the general linear group is always less than or equal to q to the power n minus 1. And from here it is also clear that if order of px is q to the power n minus 1, so this implies that this minimal polynomial, so degree of minimal polynomial becomes n. So that means that px is basically nothing but the characteristic polynomial itself, right? If order of px is q to the power n minus 1, then this minimal polynomial is nothing but the characteristic polynomial. So this implies that order of a, which is same as order of px, if this is q to the power n minus 1, then this implies that this characteristic polynomial is primitive. And in this case, this is same as, minimal polynomial. Characteristic polynomial is same as minimal polynomial. And you can prove it otherwise also. If your characteristic polynomial is a primitive polynomial of degree n, then it has to be a reducible polynomial. Therefore, it becomes a minimal polynomial, and therefore the order of a is going to be q to the power n minus 1. So this is basically if and only if. So order of a is q to the power n minus 1 if and only if chi of x is primitive of degree n. So we have proved this result. Now coming to further, so now let's look at, we have got three objects basically. So we have your polynomial ring, and here the order of, if I take any polynomial fx in this, then order of fx is less than or equal to, suppose this degree of f is n, and also suppose we have this is not equal to 0, then this. So this is one polynomial, and we have it here LFSRs of degree of order of length n over fq, and the period here is less than or equal to q to the power n minus 1. And then we have here matrices, general linear group. And here order of any matrix is less than or equal to q to the power n minus 1. So here the object that have exactly q to the power n minus 1 element, they are called primitive polynomial. And here the object which has exactly q to the power n minus 1 period, they are called primitive LFSR. And here the object with maximum possible order, they are basically in literature are known as Singer cycles. So any element here, so any matrix that has maximum possible order in the general linear group is known as Singer cycle. So let me here definition that if order of A is q to the power n minus 1, then A is a Singer cycle. So these objects here are called Singer cycles with the maximum possible period. So there is a very intimate relationship between these three objects. So what is the relationship that I'm going to illustrate now? Let me see the time actually. Oh, okay. So the relationship is that if LFSR of length n over fq is primitive, that means the period is maximum possible. So that is exactly q to the n minus 1 if and only if the corresponding characteristic polynomial of the LFSR. That means fx equal to x to the power n minus cn minus 1, x to the power n minus 1, minus c1x minus c0 in fqx is primitive. So that means the order of fx is exactly q to the power n minus 1. And of course, when we take primitive LFSR, that means it should have maximum period irrespective of the initial state. And we know that when a LFSR is absolutely periodic, it is periodic only when C0 is non-zero. So that assumption is there that C0 is non-zero in this result. And this is same as if the companion matrix. So corresponding to this, I will get the companion matrix, which I also denoted by capital T in my example. So R capital T, which is by definition is this 0, C0, 1, 0, 0, 0, C1, and so on, 0, 1, 0, Cn minus 1. This is a Singer cycle. So that means the order of CF is q to the power n minus 1 in the general linear group. This order is in the matrix group, general linear group. And this order is the order of the polynomial. So they are all equivalent actually. And of course, the proofs are, we have already seen, this is the relationship between these three objects. So there is a very nice mathematics behind this LFSRs. So we are interested only primitive LFSRs. So the primitive LFSRs are basically, they are corresponding to the primitive polynomials. So if you want to construct a primitive LFSR, just take a primitive polynomial and corresponding to that, you can design your LFSR. So this is the relationship between these three objects. So all of these things would be required when for Samrit Ram's lecture actually. So these are sort of background for his lecture actually. And he would be talking about more advanced things. And hopefully he would also be talking about some open research problem in this domain, some combinatorial problems. So I think I don't have much time now. It's already 8:54. So I think I would like to stop here actually.
Okay. Thank you, Sataj. If there are any questions, comments, we have time. People are welcome to ask.
Gurupade, I have just one query about this last slide. Can I ask?
Yeah, yes.
Sartaj, this matrix that you have shown, the second row says 1, then 0, 0, 0, and finally C1. So in the third row, what will be there? Again 1, 0, 0, 0, and C2 or?
No, it will be 0, 1, 0, C2.
Okay, so from that point onward, the 1 will be shifted to the second row column.
I made a mistake, I guess.
All along.
Oh, okay, sorry. There should be 1 here. I'm sorry, I made a mistake.
Okay. No, I had just small confusion. So
Yeah.
Thought, let me make it clear. Okay. Thank you very much for clearing it out. Okay. Thank you, sir.
Thank you.
A companion matrix, basically. Any other question or comments from anybody? I know it's late in the day, so
No, I was thinking to cover this generating function thing, but I don't think we have time now to do those things. It's already last lecture of the day, so.
second small query is like in block cipher, so many advancements are happening. So in stream cipher also, so many things are getting explored, or it's only towards its finding things with maximum cycles.
Yeah, in fact, there have been some competition also. So there was a competition that was conducted by cryptography community of European Union. So there was a project called eStream. So they have invited it was sort of open challenge to design some stream ciphers, which are good for, some of them should be good for hardware implementation and some should be good for software implementation. So that project was conducted during 2004 to 2008. And many good ciphers, stream ciphers have been suggested and in fact recommended by eStream project. So maybe I can give you that list I have with me. So in fact, let me write it. There are some important, so eStream it was the project actually. So it was conducted between 2004 to 2008. So the final result was announced in 2008, finalist. So there were some stream ciphers were good for only software, some were good for hardware. So the finalist for software were, so the name of those stream ciphers are HC128, then Rabbit, and they are all somehow based on LFSRs actually. Salsa, and then Sasimang, and for hardware it was Grain version 1. In fact, you can Google it, you will find the entire history about this. And Wiki, then Trivium, and FCSR. So there's a feed carry shift register. And some people were asking about some books actually. So these are, you know, the stream ciphers. So in fact, the TLS, which is, so TLS has been using the stream cipher RC4 so far, but there were some attacks were found on RC4. So now I think recently another stream cipher called Chacha. So that is being used in TLS. So of course the advancement are happening in stream cipher direction also, and they are good because they can be easily implemented in the hardware. So so advancements are there, and people are designing new stream ciphers, and then of course attacks are also happening. So many papers are coming on stream ciphers. But the base remains that we have to have LFSRs, some sort of combination. So there are various models for designing stream ciphers. So for example, you take several LFSRs and like this of various lengths, and then you take a Boolean function, some Boolean function, non-linear Boolean function, and it should also has to satisfy some good, nice cryptographic property, and you take this stream basically. So you take you know, output from here, this LFSR, another here, other. So and suppose there are n LFSRs, you take a non-linear Boolean function in n variables, and then finally take the output. So this is one model of designing LFSR. Another model is that maybe I should, okay, maybe here itself you have an LFSR. And you have these states S0, etc., Sn-1. So instead of taking linear feedback, you take non-linear feedback. So here this is a Boolean function basically now. So earlier the Boolean function was linear. We were taking simply C0, S0 plus C1, S1 and so on, Cn-1, Sn-1. Now I just take an n variable non-linear Boolean function. And then I take this output. So my feedback is now has become non-linear. So this is called non-linear feedback shift registers. So popularly known as non-linear feedback shift registers, NLFSR. And so there are various models actually. for designing stream ciphers. So I just gave you just 2 models. There are more models actually. So effectively LFSRs combined with some nonlinear Boolean functions with good statistical properties, high period, and large linear complexity. We need large linear complexity because if the linear complexity is less of any given sequence, then using Burley-Camp algorithm, I can find out the characteristic polynomial and I can generate the key stream. So it can be attacked. So in order to design good stream ciphers, we have to have large period, large linear complexity, and we have to use some cryptographically good Boolean functions. So I'm not sure whether I have answered your question.
No, you have answered very well. Thank you very much. I was not knowing so many things, and these are very new things. Thanks a lot.
Thank you, sir.
Can I ask something? I mean, since you showed a small portion,
yes,
what is there in your last slide? Companion.
Okay, so this was actually the proof actually. So basically companion Singer cycle, how many companion Singer cycles are there actually?
Oh, I see.
So basically, yeah. That may be useful, for later lecture by Samrit Ram. So maybe if you allow me, I can explain it a bit in a minute.
Now just show me the result. Yeah, it will have to be the same as the number of primitive polynomials.
Exactly.
Because you have this bijection.
Yeah, we have this bijection actually.
Okay, I think that is sort of clear.
Okay, yeah. So are there more questions or?
There is something in the chat box. Yeah, no, there are the only compliments I see.
Okay.
Okay, are there more questions? So if not, let us thank Sartaj. I think this is your last lecture. So thank you very much.
Thank you, sir.
All right, we are done for the day, and we have one day tomorrow. Okay, hopefully and go through that. So see you at appropriate time, 2 p.m. Indian Standard Time tomorrow.
Thank you, sir.
Good night.
Good night, sir.